Perfect. So welcome everyone. Welcome to our Skyline exam revision series in partnership with UBS. Today's session from 1:30 till 4:30 is chemistry run by me, Josh. Welcome. So just to begin with, obviously, because we're not quite at 1:30 yet, we'll just take you through an introduction. We'll go very slowly, and as people file in, we'll be getting through more and more questions and actual content. So just a bit of Zoom etiquette for today. Essentially, I just really appreciate it if you would keep your mic on mute at all times unless you're asking a question, and use the chat to ask questions. We'll also have a bit of time for Q&A using another system. So if you have any questions, about not what we're covering, but chemistry in general or university or anything like that, make sure to jot those down and you can ask them during the Q&A session. At any point, if you haven't understood something though, feel free to ask, or feel free to ask me to repeat myself. Just to double check that, can everyone see the slides that I'm sharing right now? Awesome. Okay. Absolutely fantastic. So just to give you a brief agenda of what we'll be going through today, we're not going to stick too strictly to this, but essentially just to begin with, we're going to go through, a brief introduction, our acknowledgement of country, then go through our study design changes, redox, galvanic cells and electrolysis, move on to rates of reaction and equilibrium, where we'll have a break afterwards, then go through organic chemistry, pathways and analysis of organic molecules, finish off with a bit of food chemistry, and finally just go into a bit of information about your chemistry tips and tricks and how to study effectively. So before we begin, I would just like to acknowledge the traditional custodians of the land on which we're all gathered today. I understand we're all across Victoria and other parts of Australia, so I think it's important that we all pay our respects. So I'd like to pay my respects to the elders past and present, for they hold the memories, the traditions, the culture, and the hopes for Aboriginal and Torres Strait Islander peoples across the nation. So just to give you a brief introduction of who I am, my name is Josh and I graduated from Gippsland Grammar in 2018. So I'm a rural student from a town about 3 hours east of Melbourne. I achieved an ATAR of 99.85 and one of my scores is a raw 48 in chemistry, I should say there. My apologies. So we're in a chemistry lecture, but I also took the literature lecture on Monday. And I'm currently studying a Bachelor of Medical Science and a Doctor of Medicine at Monash University. And my fun fact for the day is I once did an eating challenge on Facebook Live, and I've just got a funny picture from that, which aired to all of my Facebook friends. All right, before we begin, we do have a couple of volunteers from UBS here, Michael and Jimin. Would you guys like to introduce yourselves?
Sure, I might go first. My name's Michael Bevilacqua. I am an investment banker. I work within the kind of division at UBS that handles mergers and acquisitions. I completed VCE quite a few years ago, so I finished in 2012, and I did do chemistry as well, but my memory isn't going to serve me as well now. Post-school, I went and studied commerce and law, and I decided while I was in uni that I didn't want to go down the legal path, and I kind of fell into my current role now.
Awesome, thank you.
Hello, I'm Jimin Guo, and I'm currently working as a cadet at UBS in Sydney, and I'm in the technology department. And for my high school experience, I did the HSC in New South Wales, so that's the VCE equivalent in 2018, and I took chemistry as well. And currently I'm studying commerce and computer science at UNSW.
Awesome, thank you for that, guys. So if anyone from the audience has any questions at any point, yeah, just for any of the three of us, just write them down, and we'll have a Q&A session in the middle of the lecture where you can ask any questions about anything you'd like. So just to begin, you may or may not know that the VCAA, VCAR, who runs essentially the VC curriculum, have a study designed for each subject. And so when you're studying for exams, or when people are writing textbooks or even writing exams, they base it off this study design. And in this study design, we have 2 areas of study for each unit, Unit 3 and Unit 4. So Unit 3, Area Study 1, is about energy production. And this ranges from everything from, fuels, like undergoing combustion, to types of fuels, so our biofuels compared to our petrodiesel, also galvanic cells and redox in our electrochemical series, as well as fuel cells. Our area of study 2 focuses on the yield of reactions, where we're looking at rates of reaction in a reference to collision theory, which we'll cover a bit later, equilibrium and the Chatelier's principle, as well as electrolysis and rechargeable batteries. Unit 4 is personally my favorite, but I reckon it's the hardest part of VCE chemistry. And that's where we start talking about carbon compounds. So organic properties all the way from, organic compounds and their properties all the way from, say, our alkanes and alkenes to our esters and our carboxylic acids, as well as our analysis through IR and so infrared and nuclear magnetic resonance spectroscopy, chromatography, and volumetric analysis. And area study 2 is analysis of food. So where we're looking at the chemistry of basics of proteins, carbs, and fats, metabolism of food, and then the energy content of food and the principles of how we measure that. Now, I'm just going to stop sharing and I'm just going to bring up a set of slides, another set of slides, just as a quick Q&A sort of thing. So essentially, this is a program called Mentimeter, which we'll be using throughout the day. And what I'd love for everyone to do is you can go to menti.com and plug in that code up there, so 8433899, and give me a bit of information about how confident you feel about each of these areas of study from Unit 3 to Unit 4.
Josh, while everyone's doing this, I just want to confirm if questions do come up on the chat, do you want us to hold those over until towards the end when we'll do a Q&A session, or?
So what would be fantastic is if there's general questions about, say, UBS and like the work you guys do, or like life after high school, how to study and stuff, we'll definitely try to keep those for the Q&A. But if there's any that pop up in chat about the content we're specifically covering and the content, or like any questions about if someone needs a re-explanation, yeah, just let me know throughout the session, and then I can answer those straight away.
Yeah, great.
Awesome, thank you. All right, so we're looking pretty decent here when it comes to our spread of like confidence. Personally, yeah, I think this year with all the study design changes for 2020, so food chemistry has been made a lot easier, which is absolutely fantastic. And you guys in class should have obviously much more recently done organic chem. So I can definitely see why doing redox, galvanic cells, and electrolysis all the way in term 1, where everything was so hectic, and everything was like, yeah, all over the place. I can definitely see why we're not as confident there. But that's completely okay. Awesome. I'm just going to stop sharing and then go back to the main slides. All right, fantastic. So just to note, actually, we're not going to we're not going to do this lecture in terms of these areas of study. I think it's much easier to talk about redox and galvanic cells and electrolysis altogether, even though it's split across 2 areas of study. And we're going to save talking about fuels when we come to talking about carbon compounds, because fuels, the fuels we're using are carbon compounds, and I think it just makes much more sense when we're thinking about properties and everything like that in terms of our organic chemistry. Okay, so obviously with 2020, you'll have noticed that all of your subjects should have changed to some degree of what you're actually being examined on. For something like literature, all that's changed is the percentage of your, like how much percentage does your coursework at school contribute to your study score. But with subjects like chemistry, there's actually been a lot of overhaul. So stereoisomers, which is Unit 4 content, have been removed, along with these things called chiral centers and cis and trans isomers. So essentially, these are organic molecules that are like mirrored like as your hands are. So they look the same, but like are mirrored, and all questions about that and all content about that has been removed. So if you ever see questions about stereoisomers or chiral centers, you don't need to worry. You don't have to know that. You do have to, in the past, there's been a lot of contention with VCAR because they never mention in the study design skeletal formula, like drawing molecules in terms of their skeletal formula as compared to their chemical formula or whatever, their structure formula. But this year, they've actually made it quite clear that it is something you have to know. So we will have a couple of questions just thrown in about that. Amine and alcohol condensation has now been removed. Atom economy and percentage yield, which are just ways to calculate how much of a product we're actually getting, has also been removed. Mass spectroscopy, which is one of the main forms of spectroscopy and is very difficult, has also been removed, which is absolutely fantastic. So a lot of these changes are to Unit 4. Unit 3, so equilibrium, redox, electrolysis, fuels, has all remained the same. And then food chemistry has been dramatically overhauled. Which is super nice because food chemistry is often a bit more biological than it is chemical. So it's super good, especially for something that a lot of schools cover at the end of the year, that it's just been made up quite a bit easier. Okay, for those who haven't yet had the opportunity to actually do a practice exam, chemistry exams are pretty cool. You get your 15 minutes reading time and then 2.5 hours to answer questions. So it is a big exam. It's quite a lot of content. And we have 2 sections, Section A, Section B. Section A is multiple choice. So 30 questions worth of multiple choice, 30 answers. And Section B is our short answers, short answer response. So usually there's like 9 to 11 questions. So like this, in 2019, they had only 10 questions. And each of these 10 questions, will have like part A, B, C, whatever, like C1, C2. And then those 10 questions will in total contribute to 90 marks. So 3/4 of the exam are short answer and will require you to actually write out your calculations, write small paragraphs of like essay-like paragraphs to explain chemical concepts. And then 1/4 of the marks, so 30 of the marks out of the 120 are multiple choice, where you're just selecting answer A to D. So a lot simpler. All right. Just before we begin, and there are a few study tips for chemistry, specifically for VC chemistry, I'd like to bring up. So I think it's really important, especially as we're approaching, the last couple of months before the exam, it is vital for everyone to be doing questions from VCAR exams. So there's classic stories about people who, say for any sort of maths or science subject, who will go through their textbook and answer every single question, which is fantastic. It shows they know the skills. It shows they know how to actually do electrolysis in theory, how to construct a galvanic cell. Absolutely fantastic. But VCAR aren't assessing you as much on your ability to know stuff as they are on your ability to answer questions. And if you are not confident with your skills, the textbook is a place to go. If you want to practice your skills of, say, identifying organic molecules, naming organic molecules, identifying spectra, perfect, use your textbook. But to practice exam questions, use VCAR exams. The reason why is because exam questions are written by the same people every single year. And the more familiar you get with these exam questions, the less scary they're going to be and the less strange they're going to be actually in the exam. I would also recommend keeping a record of your practice exam scores. So personally, in year 12, I made up this Excel sheet. I started doing practice exams quite early in the year, and I didn't do well in those practice exams, but it's actually quite a bit of motivation when you see, you put down, like you say, like the 2012 VCAR chemistry exam, put down your score, and month after month, you can slowly see your score increasing. It can also tell you, when you say where you lost your marks after you've marked your exams, where your weak areas are. For example, in year 12, so back in 2018, I was positive that I knew everything there was to know about electrolysis. I was like, I may get a question wrong here or there, but that's just a silly mistake. It's not actually the fact that I don't know it. And I always thought that I wasn't very good at spectra. But when I actually went through and looked at where I was losing marks, I would never lose marks in spectra, but every single exam without fail, I would lose marks in some pretty easy stuff related to electrolysis. And then when I went back and used the textbook to study electrolysis again and do some more skills work, I was able to, boost my markup to the point where I was able to do as well as I did. There's some absolutely fantastic resources online if you need more explanation of anything. Khan Academy is a classic. MasterOrganicChemistry.com and LibraText Chem are all fantastic resources for more practice questions, more skills work, though I would recommend if you are going to be using any of these, like EdRoller as well. EdRoller is fantastic, but any of these online resources, make sure you know the study design, because as they're not based on VCE resources, they may teach you too much or too little. All right, perfect. So just to begin, we're going to go through redox, galvanic cells, and electrolysis. So what is a redox reaction? So essentially, all we need to know is a redox reaction is an exchange of electrons. It's where electrons are, given from one molecule to another. We term this as mnemonic. There's quite a few different ones you can use, but the one I personally used was oil-rig. So oxidation is loss, reduction is gain. So a redox reaction can be separated into two separate equations, an oxidation and a reduction reaction. And oxidation is where we lose electrons. So we end up with electrons as a product, and reduction is where we gain electrons. So electrons are used as a reactant. We can also use this thing called oxidation numbers to determine whether a reaction is actually redox, because there are some reactions that might look like there's electrons being exchanged, but when you actually investigate it, there's actually no exchange of electrons. So essentially, this here is what a redox reaction would look like. We have our iron solid plus our oxygen becoming ferrous iron oxide, which is essentially like rust. Our oxygen is being reduced and our iron is being oxidized. Okay, so the things to understand here, and there's a lot of complex terminology that people often struggle to get their head around. So the chemical that undergoes oxidation is called the reductant or the reducing agent. So the reducing agent undergoes oxidation, and the oxidant or the oxidizing agent undergoes reduction. A decrease in oxidation number, or electrons on the left, is reduction, so electrons as a reactant, and an increase in oxidation number, such electrons on the right, is oxidation. So an element and another thing to consider is an element that's a reactant in more complex equations can simultaneously undergo oxidation and reduction. So you've got to remember that in a chemical reaction, we don't just have one molecule. We have like millions upon millions of these molecules, and half of them could actually be undergoing oxidation and the other half undergoing reduction. Oxidation numbers are very likely to change, and that's how we know that a exchange of electrons has taken place. Oxidation numbers are more of a theoretical thing and don't really exist in any true sense of the word, but they are an indicator of where a electron has been moved. And they are not constant for any element, except for oxygen usually has an oxidation number of -2, and hydrogen usually a +1, although there are some exceptions to this rule. So if we have this equation here, so we've got sodium oxide and aluminium with water becoming this aluminium salt and then hydrogen gas, we can have a look at our oxidation numbers to determine whether or not a redox reaction is actually taking place. First things first, what I like to do is look at the oxygens. So each oxygen is going to have an oxidation number of -2. And for an entire element, the oxidation numbers should add to that element's charge. So here we've actually got no elements that have a charge. Therefore, our oxidation numbers should all add, of an entire molecule, should all add to equal 0. Next thing we're going to look at is our hydrogen. So they're all +1. So here on that first NaOH, there's +1 there. On the water, there's +1, and then that's it for the moment. So one thing we do notice is, for example, here we have 2 +1s and then a -2, and that makes sense. Because this water here, it doesn't have a charge, therefore its oxidation numbers must add to equal 0. Interestingly though, this hydrogen here has a charge of 0. It's a lone molecule, it's just H2. And so it doesn't make sense that it would have the oxidation number of that hydrogen would be +1, because if it was, then that hydrogen should be charged, but we know it's not. So when we're looking at oxidation numbers, any elements that are considered lone, so by themselves, not with any other molecules and not with any other elements and are uncharged, we give it an oxidation number of 0. And straight away, we can see here that from the OH, our hydrogen has decreased in oxidation number. Likewise, if we continue, we also have a +1 in the sodium. The thing to know about sodium, though, is sodium is creates a salt, and we don't really care about it that much. So we can see hydrogen decreases in number, and aluminium, if we have a look, will actually increase in number. We go from 0 here to requiring it to be a 1 or a 2 here, because it's because it is actually part of a molecule. Therefore, we know that aluminium is undergoing oxidation, and then the hydrogen is undergoing reduction. Okay. So one of the big things they ask us in VC chemistry is balancing half equations. So we use a method called cohes. So K for key elements, O for oxygen, H for hydrogen, E for electron, S for state. So it's just a little mnemonic to use to actually be able to work out how to balance equations. This is particularly important because sometimes they can give you some crazy questions and expect you to balance them. A classical example is giving you an equation of the oxidation of something like ethanol into ethanoic acid, and then they say, okay, balance this equation. And you can sit there for as long as you want trying to work out numbers, juggle numbers, saying, okay, well, we're going to do 2 lots of this ethanol and that will create however many other molecules. And you can sit there for a long time and it will be really hard. But what simply you can do is break a big equation down into its 2 half equations, and you can actually balance them from there, which is actually a super easy thing. And you'll find a lot of people will lose marks in the exam because they don't know this tip. So when we do have half equations, we have to balance them using this method. So I'm going to use the example here. It's ethanol has reacted with dichromate, which is a strong oxidizing agent, to produce ethanoic acid and a chromium ion. Okay, so to begin with, we know that our dichromate must become chromium. That makes sense, because they're both the same molecule. And that there is our key elements. Our chromium becomes, our chromium and our chromate has got to become chromium, essentially. Just as we know the ethanol is going to have to become ethanoic acid. So to begin with, key elements. Okay, well, we can see that, we just got a question there. That's all right. We can see that we have in our first line, we have Cr2O7 becomes Cr. Well, key elements here, first off, we've got to balance our number of chromiums. So we need 2 chromiums on the right-hand side. Therefore, we have Cr2O7 becomes 2 chromium. Issue here now is that we have O7 on the left and we don't have anything on the right, and we need to somehow find a way to balance this oxygen. The classic stitch-up chemistry students make is just adding O2. We can't do that because we don't know what sort of environment it is. We don't know if there's actually oxygen in the environment, but what we do know is if it's an aqueous solution, which it always will be, there will be water available. So whenever we need to add oxygen, we simply add water. So to balance the 7 oxygens on the left, we add 7 waters on the right. So now we have dichromate becomes 2 chromium ions plus 7 waters. Issue here now is that we have 14 hydrogens on the right and none on the left. So now we jump into our H of cohes, hydrogens. So now we're going to add 14 hydrogens to the right, and we can't add hydrogen gas. We don't know how that works, but we can add hydrogen ions, H+. Now, if anyone can remember back to unit 1-2 when we talked about acids and bases, well, H+ is simply our protons, which is essentially the atom that we're donating when there's an acid. So you can tell that this equation actually occurs in a very acidic environment. All right, nearly done here. The only issue is the charges so we have the same number of elements on the left and the right. The only issue is we need to have the same amount of charge on the left and the right, which is where our electrons come in. So on the left, we have in total, to begin with, -2 plus 14. So that's positive 12. On the right, we've got positive 6. So the difference between positive 6 and positive 12 means that we have to take away 6 on the left or add 6 on the right. Well, we can't find a way to add charge without adding like more hydrogens, for example, but then we're not going to be balanced anymore. So we add electrons, which each have one negative charge, onto the left. So now if we see on this bottom line here, -2 plus 14 take 6. So 14 take 8 is equivalent of 2 lots of +3. So positive 6. Therefore, we've balanced it. We've gone to electrons. The final thing to note is states. Now, I haven't included states in this equation here, but we will a bit later. Electrons do not have a state. Electrons aren't an atom. Like, they're just electrons, so they don't exist in states, but everything else does. Be careful that, like, they're usually all aqueous. Be careful that you don't put water as an aqueous solution. Water is a liquid. The next thing now is we've got this first half equation. We've got this this reduction reaction here. We know it's a reduction reaction because our dichromate is our oxidizing agent. So oxidizing agent undergoes reduction. Next up is our ethanol becoming ethanoic acid. All right, straight away to look at it, we have 2 carbons on both sides, so we don't need to balance carbons. We have 6 hydrogens on the left and 4 on the right, and 1 oxygen on the left and 2 on the right. So what are we going to do? We're going to add 1 oxygen to the left, so H2O. Issue here now is we've got 8 hydrogens on the left and only 4 on the right. Therefore, we're going to add 4 hydrogens on the right. That gives us here H2O. So ethanol plus H2O becomes ethanoic acid plus 4 hydrogen ions, 4 protons. Now the charge on the left is 0, charge on the right is positive 4. Therefore, we jump to our electrons. We have to add 4 electrons on the right. That there is our 2 final equations, our reduction reaction up the top and our oxidation reaction down the bottom. Now, there are obviously, when we talk about galvanic cells, much easier equations. For this here, like, the thing to understand about chemistry is that what they're trying to do is relate together all different parts of the curriculum into one thing. So this is why I've been using an organic chemistry model to go through this. We now need to continue on with this to actually bring the 2 equations together to balance it fully. So again, we have our ethanol reacted with dichromate to produce ethanoic acid. Here are our 2 equations. Now, in a proper full equation, you will never see electrons. So we've got to figure out some sort of way to get rid of the electrons. We therefore know that these 2 equations must be in ratio. So what common number does 6 and 4, like what common product can they create? Well, the smallest one is 12. So if we multiply the top equation by 2 and multiply the bottom equation by 3, both equations will have 12 electrons, which means the electrons will cancel out when we add those equations together. So this here is where it gets a bit tricky. Okay, so we're going to have, starting with our top equation, we're going to have 2 dichromate, so there's a 2, plus 28 hydrogens, plus 12 electrons, which are going to be cancelled out, so that's fine, becoming 2 times 2 chromium, which is our 4 chromium there, and then 2 times 7 waters, just our 14 H2O there. For our bottom equation, we're going to have 3 lots of ethanol plus 3 times 1 lot of water becomes 3 lots of ethanoic acid plus 3 times 4 lots of protons, which gives us 12. Now, if we leave it like this, we haven't got the marks that we need. You could have done all this work, you could have, like, for a 4-mark question, but you still haven't gone all the way. We still need to continue going and cancel stuff out. So as we can see, just grab some red here, we have 12 hydrogens there, which will help cancel out some of these. I believe that should be 16. I do apologize. That one there should be 16. I apologize about that. And we have our waters that cancel out here and here, so it brings us down to 11. And then that there will be our full equation. Awesome. Okay. The other big thing to note, and the thing they can sometimes throw in, which a lot of chemistry students actually haven't learned, is that redox reactions don't necessarily take place in an acidic environment. They can also take place in an alkaline environment. But we can't have an alkaline environment if what we're using is hydrogen ions, because hydrogen ions suggest a acidic environment. So we use protons to show redox titration is happening in an acidic environment, like so. So I'm just using what we used earlier from that first dichromate reaction, so 14H plus and 7H2O. The issue is we don't have H plus. If you're ever asking you to solve a redox equation, like write up a half equation that happens in a base, you just need to do the exact same steps of cohes. So KOH, but when you get to hydrogens and add these 14 in this example, 14 hydrogen ions on, we just include an extra step. We have to include, so for every hydrogen ion on in the equation, we're going to add the same number of hydroxide ions to both sides of the equation. Now that's okay, if you add something to one side, it will cancel out on the other, but it's just going to do a few things that makes life a lot easier for us. So our 14 hydrogen ions plus our 14 hydroxide ions, well, what does hydroxide and hydrogen create? Creates water. Therefore, we're left with dichromate with 14 waters becomes chromium plus 7H2O plus 14 OH. This here is the half equation, almost, for a redox reaction in a basic environment or alkaline environment. Now we have to balance the sides of charge. On the left, we've got -2. On the right, we have +6 minus 14. Therefore, we're left with 6 electrons on the left. And as you can see, this here is almost an identical, like the 6 electrons are still say the same from the acidic environment, still the same spot, still the same number. The only difference here is that instead of H plus, we have got OH negative and the water has just changed sides. The other thing to note is that I've just used dichromate in this example because we used dichromate to begin with. In actuality, dichromate is a chemical we use for almost exclusively for organic chemistry, which always will require acid. So you won't actually ever see dichromate being used at the base, but you will be seeing other chemicals like used in a basic solution. So I've just used this as an example for basic redox reactions. All right, now we're going to jump onto electrochemical series. So electrochemical series is pretty cool. And if you guys don't know, you actually have the entire electrochemical series in your data booklets. I'd really recommend, if you haven't seen them before, look up your VCE chemistry data booklet on Google. This is a booklet of like 28 pages of pure information that you get to use in the exam. So from left to right, we have our reduction reactions, and from right to left, we have our oxidation. These are reversible reactions, so they can go either way depending on the environment. Our strongest oxidants are on the top left, and the strongest reductants on the top right. A reaction, when you have two chemicals or two or more chemicals together, a reaction will occur spontaneously if the strongest oxidant is above the strongest reductant. So if we're going down like a slide from left to right, so if our, like from here, if our strongest oxidant is up towards the top and the strongest reductant we have available is towards the bottom, that will occur spontaneously. But if our strongest reductant is actually above on the electrochemical series, above our strongest oxidant, then we're actually going to require energy to, for the equation to occur, which means that's no longer a galvanic. We can no longer use it in a galvanic cell. We have to use it in an electrolytic cell. The other thing to note that, oh, sorry, let's go back. The other thing to note that VC students often get messed up is that they think this electrochemical series is an indication of how fast the reaction occurs. That is not true. And in fact, VCAR in the past has actually tested whether or not students know this. And they will ask something about, what does the electrochemical series signify, or can we tell the rate of reaction with electrochemical series, or which will have a higher rate of reaction and give two equations. The electrochemical series does not tell us the rate of reaction, and it also doesn't tell us the position of reactions in terms of their strongest oxidant or reductant in conditions other than our standard condition. If you note on the top right, we have our standard electrode potential in volts at 25 degrees Celsius. So if we're not at 25 degrees Celsius, this electrochemical series can actually change. So there's technically an electrochemical series for every temperature. That's just another thing to look out for. So if we were to do an experiment at a temperature different from that isn't 25 degrees Celsius, well, then we could get results that are different from what we predict. That's just something really important to consider. And again, this only represents what reactions will theoretically or potentially occur, but there have to be other chemical stimuli and also physical things to have to occur for a reaction to actually exist. So for example, we could have two chemicals that are near each other, but for a reaction to occur, as we're going to cover later in collision theory, they need to hit each other. And if they are unable to touch each other, or say an ion is moved away due to a charge, well, then a reaction won't, in fact, occur. Okay, here is our galvanic cell. Classic, we have our anode on the left and our cathode on the right. Oxidation occurs at the anode, always, and reduction occurs at the cathode. Simple mnemonic for this, I would use was like an ox, so you'd have like an ox, and then red cat. So red cat, reduction, cathode, and ox, anode, oxidation. Bit of a silly one, but like I really felt like that helped. And we can see at the anode where we're producing electrons, electrons go through this external circuit and then go into the cathode. So oxidation occurs on the surface of the electrode, usually resulting in the consumption of metal, which will mean this electrode will start to wither away. Reduction occurs on the surface of the electrode, usually resulting in the deposition of metal. And the salt bridge here completes the internal circuit. And I'm just going to cover what the salt bridge actually does and why it's so important in just 1 second. So in a galvanic cell, the anode is a negative electrode that electrons move away from and into the external circuit, which is a wiring around the galvanic cell. The cathode is a positive that electrons move towards. The issue here is that in the oxidation half cell, if we're using metals, for example, we're essentially producing, like, from a metal ion and electron. And metal ions, as we know, are charged. They're positively charged. So as this reaction continues, we get more and more positive ions in the solution, and the anode is negative. So this is slowly making the anode more and more positive. Likewise, in the reduction half cell, the same thing's happening, but just in reverse. It's becoming less and less, more and more, less and less positive. And if we were to leave it with no salt bridge, and we just to say this happens, well, then our galvanic cell, like what is our battery, would just stop working straight away. So the accumulation of charge, this is what you'd have to use if they ask you about it in the exam. This phrase is super useful. The accumulation of charge results in the cessation of action of the galvanic cell. Just a simple sentence to remember that you can always write down. The salt bridge contains an unreactive ion salt, and this connects the two cells. And what happens is anions move to the anode and cations to the cathode. So quite simple to remember, and cat to cat. So the negative charge of the anions will move to the anode where it's accumulating positive charge, which means the charge that's accumulating is ignored, and on the right where our cathode is, where it's getting less and less positive charge, well, the cations will migrate there, keeping that positive charge stable. The issue here is the electrolyte, the salt bridge, must be able to first off conduct electricity. That's simple enough. But sometimes one of the questions they ask is they might give you a salt bridge that contains a metal or contains salts that actually will interfere with the reaction that's occurring. So it's really important to look out for this. But most of the time, potassium nitrate is what's most commonly used. Awesome. Okay, so general tips and tricks. Water is usually present, and water may be a reactant that interferes with cell function. Water is on the electrochemical series, which must be considered if series are present in an aqueous state. Also, hydrogen ions and hydroxide ions may be possible reactants. And if the species aren't metal, so if we can't use a metal electrode, we'll use inert electrodes. So, for example, if we're using chlorine, producing chlorine gas, well, we can't have an electrode. We can't have an electrode that will also react, because that won't be guys, just to remind you, if you don't mind keeping your mics off just while we're presenting, that'd be awesome. But essentially, inert electrodes include platinum and graphite. Those are the main ones, and they typically won't react in a galvanic cell. And reactants that are, let's say we let our reactants accumulate, especially if they're a gas, like chlorine gas, they can actually interfere with the cell function again. So there's actually a lot of things we have to do to make sure our galvanic cells are fine. So when we're looking at a question, make sure that reactants are removed. And if something messes up in the question, well, then you have to consider, well, where are the reactants? Where are the products as well? Sorry, that's what I mean by products. Okay, I have a simple question here that I'm just going to run through, like the sort of thing that you might often see. Actually, I'll let you guys do this one. So I'll give everyone about 5 minutes to go through this question, see how much you can get done. This is a pretty simple question that essentially is a bit of summary of what we've just covered. So a solution of nickel 2 chloride and copper 2 chloride are poured into into half cells containing a strip of nickel and a strip of copper respectively. Those are our electrodes. A salt bridge is set up and a set of wires with a voltmeter used to connect them. Write the overall equation that occurs. Draw the galvanic cell, so give it make a drawing and annotate the most important functions. Describe the function of the salt bridge and calculate the voltage. So I give you guys 5 minutes. If anyone has any questions, feel free to type them in chat in the meantime. But we'll get back to going through these answers in 5 minutes. So I've given you guys 5 minutes to do it. It may cut it a bit short, but one thing to note is that you get in the exam a total of 2.5 hours, and with a total of 120 marks. So if we work that out, 2.5 times 60, so it gives us 150 minutes, and we divide that by 120 marks, we're only really able to spend about a minute and 15 seconds, so 75 seconds per question, which is actually pretty tough. But I really think that's not a great way to think about it, because there are some questions in multiple choice, for example, that you can sit there in reading time and you can go through and you can understand straight away. They might be talking about enzyme action or the difference between a carbohydrate and a protein, and multiple choice, super simple. You can look at it and most of the state will get that correct. There are other questions in multiple choice though that may require you to do working out for 4 or 5 minutes. So not all marks are equal is something I'd like to stress. And the reason why I talked a lot about doing more and more exams at the start is so you get used to exam timings and get used to how much time you're going to be able to spend on each type of question. Because if someone who's good at, say, organic chemistry, they might only need 30 seconds per mark for organic chemistry questions, but they might need 2 minutes per mark for electrolysis. So don't live. One of my recommendations is don't live off that time per mark. I think that's a really bad way of going about it. But hopefully everybody has at least done the first little bit of the question, and we'll go through right now. And when it comes to Mentimeter, yeah, sorry about that, guys. So we're going to save Mentimeter for our Q&A sessions. If you have any questions about this exact, what we're going through on the slides, feel free to either private message myself or one of the volunteers, or just post in the chat on Zoom. So yeah. And when we go to Mentimeter is when we're going to be doing more of a Q&A sort of session. All right, okay, so to begin with, write the overall equation that occurs. Now, for a sort of question like this, we want to identify all available reactants first. Okay, so well, what do we have? We have water, and that's a really important one to consider. We have water up the top here, water here, and water all the way down the bottom. So water seems to be a very weak oxidant and weak reductant. We have nickel ions and nickel solid, and copper ions and copper solid. As we know, the strongest available oxidant will react with the strongest available reductant. Strongest available oxidant is copper ions, and strongest available reductant is nickel solid. Therefore, I apologize about the syntax there, that's messed up a bit, but our copper ions will become copper solid, and our nickel solid will become the nickel ions. And because they're both positively charged by 2, we don't need to do any sort of crazy multiplication, and simply we have nickel solid plus copper ions becomes nickel ions plus copper solid. Super easy. Make sure to include states. You won't get the mark if you don't include states. Draw the galvanic cell. Now, I've done a very crude drawing. I apologize, but they're not expecting you guys to be artists. Essentially, at the anode, we're going to be having our oxidation reaction, and at the cathode, our reduction reaction. Make sure to include the external circuit and voltmeter and the salt bridge. All right. Part C was described as function of the salt bridge. So again, just going over what we talked about earlier, the salt bridge contains a conductive ionic salt. As the oxidation reaction in the anode produces more nickel 2 ions, the charge in the half cell increases. Likewise, the reduction reaction at the cathode results in the charge of the half cell decreasing due to the copper 2 ions being reacted or being removed. The cation of the ions of the ionic salt migrates to the cathode, and the anions migrate to the anode, which stops the accumulation of charge. That's essentially all you need to mention. When they're asking you a question, make sure you reference the actual question. So here I've referenced nickel and copper. You can definitely get away with using a very general explanation, but to really show if the examiners are in doubt that you know what you're talking about, make sure to reference, say, the nickel and the copper. Calculate the voltage. So the expected voltage is just going to, we don't need to use any equations like Q equals VIT. For a galvanic cell, the expected voltage is simply the difference in voltage between the 2 points, between our two electrochemical series. So our highest voltage minus our lowest voltage of these two half equations. So our highest voltage is positive 0.34 and our lowest is negative 0.25. Classic stitch up here is adding them together and getting your 0.09. No, we add them together. We minus one from the other. Minusing a negative is going to be addition. Therefore, our answer here is 0.59 volts. If we were to calculate charge, we would also need, so I had a question earlier about like, we don't have time, so we can't figure out voltage. No, we can figure out expected voltage, but to figure out charge, we need we need time, essentially. So voltage we can figure out with just the electrochemical series. Awesome. Okay. The next thing I just want to cover is fuel cells. So fuel cells are galvanic cells, and they're actually pretty cool and pretty nifty. And that's something that you know, a lot of companies are investing a lot of time and research in. They're specialized galvanic cells that generates electricity from the oxidation of fuel by oxygen. Now, typically, you know, you could have methane coming in as your, so one reactant will be oxygen, the other could be methane, it could be ethanol, it could be, you know, a petrodiesel, but it's essentially just, when we burn a fuel, right, we're burning with oxygen to produce energy. There's energy that's been released in the form of heat. The issue there is that it's actually not very effective. Like when we actually burn burner fuels, that energy like heats up the water we produce to spin a turbine, which produces energy. So there we've converted chemical energy to thermal energy to kinetic energy to electrical energy. In a fuel cell, we cut out all the middleman processes. We're converting straight from chemical energy to electrical energy. So these are really efficient. We have reactants that are continuously fed into the system, so we keep pushing them in, and products continuously removed. Therefore, we produce a continuous electrical supply. And it also doesn't need recharging because it's not a battery in the sense that, you know, like with our batteries where our electrodes will eventually erode, because we're continuously putting in reactants, we won't ever need to recharge it. One of the questions they like to ask, VCAR, they ask, what are the pros and cons? Now, there's a lot of pros to this, you know, super efficient. Actually, it's like fairly cost effective, and we're producing a continuous electrical supply and we don't need to recharge. The issue is, if you imagine having this in a car, well, we also need space. We need space for the fuel cell, but we need space for where all the reactants can come from. And we've got to remember, one of our reactants is oxygen, but the other is a very potent fuel like hydrogen gas or methane or ethanol. And you can imagine in a car, if there was to be, say, for example, a car crash where all of this very potent fuel is released into the atmosphere, well, that can cause, you know, explosions as well. So that's just something else to consider, that although they're fantastic, they're not actually that practical for like commercial and civilian use right now. Electrolytic cells are pretty cool. So electrolytic cells are essentially like when we have a non-spontaneous reaction, so the reverse essentially of a galvanic cell, we pass a current into the electrolytes and we make a reaction happen, a reaction that normally wouldn't happen. So again, on the electrochemical series, we have that difference in voltage. So the potential difference of the battery, so the voltage of the battery, we've got to remember has to be higher than the potential difference between our two half equations. That's a classic VCAR question where they get you to set up an electrolytic cell, and they say, okay, you put a 0.5 volt battery into the system, why doesn't it work? And people will be like, oh, maybe there's water involved, maybe there's gases that shouldn't be there. No, check the battery, and 9 times out of 10, the battery is actually not strong enough to actually produce this equation. And where galvanic cells convert chemical energy to electric energy, here we're transforming electric energy to chemical energy. So oxidation still occurs at the anode, reduction still occurs at the cathode, but here it's changed. The anode is now positive, and we connect it to the positive terminal of the battery. Cathode is now negative, and we connect it to the negative terminal of the battery. We also use this principle in electroplating. So my chemistry teacher in year 12 he was a amazing teacher, but he had this habit of always losing his stuff. And he told us a story about where after he got married, he would always lose his wedding ring. And you can imagine, like, that's a lot of money gone if you're losing your wedding ring every couple of months. So what he did is he bought a very cheap iron ring, like ferrous iron, and went to a company where what they did is they used that iron ring as an electrode, and they have gold ions in the solution. And this is a principle called electroplating, where when we put electricity in, the gold all migrates to that electrode, and then the gold ions with the electrons become solid. And so essentially it's got an iron ring, but wrapped around it is gold. So it looks like gold. Another principle of this is a classic one in Victoria. So it's something ridiculous, like 1/3 of Victoria's energy output goes towards a plant in Portland, I believe, where they produce aluminium. So it's actually electrolytic cells and like electrolysis is actually a very important industrial technique. Okay, so just to briefly run over Faraday's laws, we have charge equals the number of moles of electrons times by Faraday's constant. So Faraday's constant is a charge on 1 mole of electrons, and that's 96,500 coulombs. Coulombs is charge. So it makes sense that the total charge of a system is going to be the number of moles of electrons times by the number of charge in 1 mole of electrons. Pretty simple. Our first rule is that the mass produced or consumed at an electrode is directly proportional to the total charge that passes through the system. Okay, so anything that changes charge will change the amount of substance produced or consumed. Okay, if we change the number of electrons going through, we're going to change the charge, which changes how much energy, how much mass we're producing or consuming, which makes sense because electrons is essentially related to electricity. And if we decrease the electricity, like there's less voltage or less less time, well, then we're going to be producing less mass or consuming less mass. Then that there, so Q equals IT and E equals VIT. Those are just equations that are on your data booklet. Rule number 2, mass deposited or consumed is inversely proportional to the charge carried by equivalent metal ions. This makes sense, right? So for like ferrous iron that has that's +3, well, it's going to require 3 moles of electrons to produce 1 mole of solid iron. But for an iron ion that's +2, that's only going to require 2 moles of electrons. So therefore, if we give both of those iron ions the same amount of electrons, the one with the higher charge is going to produce less solid iron. So mass deposited or consumed at electrodes, not at electrolytes, is inversely proportional to the charge carried by equivalent metal ions. So the higher the charge, the less stuff we're producing. All right, just to finally sum this up, we've got secondary cells. Secondary cells are essentially where it's a galvanic cell, a discharge, and then recharge occurs, where we connect a battery in and it just reverses the equation. So it's a rechargeable battery essentially. The thing to note here is that where we have our electrode, say breaking up a little bit, and then our ions migrate back to reform it, this can actually damage the electrode, which means rechargeable batteries will, over many life cycles, actually die. So just because a cell is secondary and it's a rechargeable battery doesn't mean you can keep using it. You will eventually need to replace it. All right, so here is a question from the VCAR short answer exam. This is question 7. And essentially we have a zinc cerium battery, which is a commercial rechargeable battery that comprises of a series of cells. During recharging, we use like solar cell panels or energy from wind farms. And during discharging, we create energy, which is supplied to an electric grid. So essentially we're like harnessing energy almost. The electrolytes are stored in 2 separate tanks and are pumped in and out. We use, they're also immersed in 1 molar methanesulfonic acid rather. And here is a diagram of the cell. We have 2 half equations. Our questions here are write the overall equation and determine the theoretical voltage. Here is a VCAR classic stitch-up. We're so used to the electrochemical series for the top reaction to occur as a reduction reaction, so from left to right, and the bottom to occur from right to left, that we sometimes ignore the charge. But remember, the higher the charge is, so the voltage is, the higher it actually is in the electrochemical series. So because this here is a higher voltage, this equation here is going to go that way, and that one here is going to go this way. So first things first, highest voltage value is the reduction reaction in discharge. Therefore, we have only 1 electron for every 2 at the top, so 1 electron at the bottom. Therefore, we've got to multiply our bottom reaction by 2. So we have 2 lots of C sulfonic acid plus 2 lots of hydrogen plus 2 electrons. Now we're going to go take from the other side of the top, plus 1 lot of zinc plus 1 lot of 2 lots of this this chemical here. That's our reactants, and our products are just going to be the inverse. So our 2 lots of this one here and 2 lots of that one there. So of our bottom reaction and of our top one, 2 lots of the zinc compound and 1 lot of zinc compound, 2 lots of the hydrogen and 2 lots of the electrons. Now, if we start cancelling stuff out, we are 2 hydrogen ions and 2 electrons cancel out in the reactants with the ones in the products, and also our 2 lots of metasulfonic acid cancel out from the top to the bottom, from the left to the right as well. Therefore, we're left with 2 that looks very similar, but we're left with 2 lots of this cerium compound with a charge of 4 there, plus zinc, plus 2 lots of the charge of 3, plus zinc as well. So we can see that actually all adds together. Because this is essentially the same thing each time, this here is essentially like a salt, this bit here. So we can actually divide that up. And that means we begin with, because there's a 4 there, we have a charge of plus 4, and here there's a 3 there, that means that's a charge of plus 3. So we can see that this is definitely an exchange of oxidation numbers, therefore an exchange in electrons. It's a pretty hard question, that one. And our theoretical voltage is 1.67 minus negative 0.76, which gives us 2.4 volts. Our next 2 questions are write the ionic equation occurring at the positive electrode during recharging, and other than transporting ions between electrons, describe one function of the membrane. Okay, positive electrode during recharging is the anode, during discharging is the cathode. Got to remember that one. So it's the anode. What equation is happening at the anode? Oxidation reaction, therefore it's just this reaction here from the previous data. The membrane in a fuel cell actually acts as a salt bridge, but that's already been discussed in the question. It's transporting ions between different compartments of the cell. The membrane also prevents the oxidant and reductant from coming into direct contact. If we had our 2 chemicals that would hit each other and would react, well, that would produce heat, would produce thermal energy. That's energy wasted. When we have them separated, well, they have to transfer their electrons through an external circuit, which is what actually generates the electricity. And again, to prevent the release of thermal energy in the cell, which would destroy it. So that's why the membrane is so important. All right, we're going quite well time-wise. We're just going to cover a bit on equilibrium and rates now. Okay, so just to begin with, we're going to talk a bit about collision theory. And this theory states that molecules must collide with enough force and in the correct orientation in order for a reaction to occur. So when colliding, some of the kinetic energy, so some of the movement energy, becomes vibrational energy, so energy that makes the bonds between atoms vibrate. And the reaction can only occur when the vibrational energy is greater than the activation energy to break bonds. So if you look at this image here, we have our two chemicals, and if they're moving too slowly, so they don't have enough kinetic energy, they're going to hit each other and then just move away. They need a certain amount of energy for a reaction to occur, and we call that the activation energy. Likewise, if they're facing the wrong way, well, they're hitting with enough force, but they're not hitting each other in a way that will actually break the bonds. The only way for a reaction to occur in accordance to collision theory is for there to be enough energy and there to be a correct orientation, which, as we see in the last image there, produces the best outcome, which produces the actual reaction. So rates of reactions, only a small proportion of collisions actually result in a reaction, as we've seen. So therefore, to increase our rate of reaction, which is very important, say if we run a factory and we're producing chemicals, we want to make it fast, well, we need to increase the frequency of collisions. So I'm just going to stop sharing, and there's just two things I'm just going to show you on Mentimeter. So give me 1 second. I'm just going to pop up a quick Mentimeter here. Just going to move this. So feel free to log back onto here and maybe put some ideas in as to how do we increase the rate of reaction. This is a simple concept, but often it's like something we can forget quite easily. Increased temperature, absolutely fantastic. Yeah, increased temperatures, yeah, there's a classic one. Catalyst as well, awesome. Increase the surface area, awesome. Increase pressure, increase surface area, decrease volume. Yeah, these are all absolutely fantastic, everybody. Awesome. Okay, I'm going to go back to our PowerPoint now. Just give me 1 second. Here we are. Okay. So, as people have stated, we can increase the surface area, increase concentration or decrease volume, increase temperature, or add a catalyst. The way I would always explain it is in the following methods. Well, for rate of reaction to increase, we need to either increase the number of successful collisions, or just increase the number of collisions, because a reaction occurs when bonds broken increases. So when we increase surface area, we have more reacting particles coming into contact, increase the number of collisions, therefore number of successful collisions increases, therefore rate of reaction increases. Increasing concentration / decreasing volume, particles collide more commonly, increasing number of successful collisions. Increasing temperature is a tough one. A lot of people say, oh, probability of collision increases because they're going much faster, so they're more likely to hit each other. Well, that's true. You're not going to get the mark here if they ask you about temperature unless you say particles collide with more energy. So a greater proportion of particles, when the temperature's been increased, have energy greater than the activation energy. And activation energy is the energy required for a collision to be successful. A catalyst is also a cool one. A reaction requires energy for a collision to be less energy for a collision to be successful. So we decrease the activation energy. And we see this on this Maxwell-Boltzmann curves. So when we have a catalyst in here, well, here is essentially this graph here is the amount of energy that all of our particles have. So when we have an activation energy, normally, only a very small proportion of these particles, when they collide, will actually react. So when we actually decrease activation energy, we can see now all of that area of particles, when we have a catalyst, will actually react. That's why the rate of reaction increases. Conversely, we can increase temperature. So here we have T1 and T2. T1 and T2 have the same area, which they represent the same amount of particles, but because T2 has a higher temperature, the average temperature is shifted more to the right. Therefore, while the activation energy remains the same, a greater area of particles, essentially a greater number of particles, have the energy required for a reaction to occur. That's why rate of reaction increases with temperature. Absolutely fantastic, awesome. Okay, here we have a rate of reaction question. I'm actually just going to zoom through this one because I really want to get onto our equilibrium stuff. So we have an experiment where we have a simple metal that's combined with hydrochloric acid to produce a salt. We have Jonty, and he combines the metal with 0.05 molar hydrochloric acid. He then repeats the experiment with 1 molar acid and beaker of identical volume. Explain why more bubbles are seen in the second solution over the same period of time. Also, at the same time, Mark increases the heat of his 0.05 molar hydrochloric acid, then adds the metal. Explain the effect this will have on rate of reaction. Pretty simple. Question 1, part A. Well, in the first part, the experiment will result in a metal salt and hydrogen gas being produced. So that's why there's bubbles, because there's hydrogen gas being produced. More bubbles appear in the second experiment because the concentration is increased, increasing the number of collisions occurring, increasing the number of bonds broken, increasing the rate of reaction. That's all we need to do. Simple as that. For B, where we increase temperature, increasing the temperature of the solution increases the average kinetic energy of the particles, meaning that more particles collide with the energy greater than the activation energy. There are more successful collisions, increasing bonds broken, and therefore increasing rate of reaction. That's how we smash out those rate of reaction questions. Just follow that simple formula. All right, equilibrium now. This is some fun stuff, and it's actually quite hard as well. But something you have to understand is that the majority of reactions we see in nature, when we're putting two chemicals together, are reversible. They can happen one way and they can happen the other. If there's sufficient energy available, where reactants are colliding to create products, products are colliding to make reactants. And this makes sense in the sense that we have a bunch of reactants lying around and they're bumping into each other, colliding. There's less and less reactants, and slowly there's more and more products. And the products then are bumping around, they're hitting each other, and every now and again, those products hit each other with the right energy and the right orientation that makes a reactant again. So at some point, we're going to reach a concentration of products and reactants that's in perfect balance. There's reactants still becoming products, but that's balanced out by products becoming reactants. So there's no net change in concentration. And this is equilibrium, where the rate of forward reaction equals the rate of backwards reaction. So collisions are still occurring, but the net concentration of products and reactants doesn't change. So if the rate of the forward reaction is less than the rate of backwards reaction, is greater than, the reaction's still taking place forward in the way we expect it to. But if our rate of reaction of the backwards reaction is greater, well then we're actually going to be having a net push backwards, and equilibrium is where our rate of reaction of our forward and our backwards reactions are equal. So there's no net change. All right, we have this equilibrium constant, and this essentially expresses like a relationship between concentration of reactants and products at equilibrium. And this is down here on the bottom right, where C and D is our products and A and B are our reactants. So the coefficient, so what we do is we put the concentration of our products in the top, concentration of our reactants in at the bottom, and we raise each of those concentrations to the power of the coefficient. So for example, if we have if we're producing, for example, 2 nitrous oxide, well then in our equation, we're going to be having the concentration of nitrous oxide squared, because we carry that 2 as a coefficient over to a power. We also have a thing called Q, which is a reaction quotient, calculated in the exact same way, but doesn't give an indication of equilibrium. So if Q is less than EK, well then that means if Q is less, that means Q has a greater amount of stuff on the bottom, which means greater reactants, which means we're going forward still. And if Q is greater than our equilibrium quotient, equilibrium constant rather, then our backwards reaction is favored. An important thing to notice here is that units can be extrapolated from the calculation and will change depending on what reaction, which I'll cover in a second. And other thing to note is that we don't actually include water in our calculations. All right, so our practice questions here, we have AgCl becoming our 2 ions, and then ethane combusting to produce energy. Here, for this first one, we put our products in the top, so Ag plus and Cl minus. Our concentration is measured in molar. So we have molar times molar divided by molar. Okay, well, M times M divided by M is just M. So that there is our unit for that value of K. For this second one though, we set it up a little differently. Remember, we don't include water, so the only product we're including is CO2. And as I mentioned earlier, we take that coefficient and we raise the concentration to that power. Likewise, at 7 becomes to the power of 7, and the 2 there becomes to the power of 2. Now we got to like work out our coefficients. Sorry, work out our powers. So we have 4 on the top, and we have a total of 9 on the bottom. So 2 plus 7. So 4 divided. So something to the power of 4 divided by something to the power of 9. Sorry, something to the power of 4 divided by something to the power of 9 was 4 minus 9, as you might remember from maths. So that gives us a unit of m to the negative 5. Just to clarify, relating to Q and EQ, sorry, Q and K of EQ. K of EQ is going to be a set number at a certain temperature. It's set, and that tells us when equilibrium has occurred. It tells us the relationship of the products and reactants when equilibrium has occurred. Q is a bit different. Q is the same formula, but it's just can be used anytime, and it just gives us an indication of if it's greater than K, well then our backwards reaction is happening, and if it's less than K, well then our forwards reaction is happening. So K will never change unless we change temperature, whereas Q is just the value of the relationship between concentrations at this very point. They don't necessarily have to be in equilibrium. All right, and so just to give you an example of what can happen is Kc, so another way of running K of EQ, stays a constant. So when we change something in this equation, like change something in a solution, so the solution's at equilibrium, and we say remove something, let's say we take out a bunch of product. We take out a bunch of product C. Well, that there means the C is going to decrease. That means this, because C is decreased, the value of K is decreased, but K, or rather the value of Q at that point is decreased. But we need to get back to K. So what happens is we favor the forward reaction. So we produce more C, we produce more D, and then we consume A and B. So now we're going to have a different amount of concentrations of A, B, C, and D, but when we put them into the equation, they're going to produce the same number. That's the tricky part. All right, so changing the system, the Chatelier principle. So essentially, all systems will tend towards equilibrium. All systems of chemicals want to reach equilibrium. When we add more reactants, well, therefore, with Q, we're decreasing Q. Therefore, adding more reactants will favor the forward reaction. Increasing pressure will favor the side that, with the least amount of molecules. Let's say we are using one chemical to produce four separate molecules, so breaking it down. Well, when we increase the pressure, our system is like, oh no, now there's too many molecules in the system, you want to go back. You take the backwards reaction. But let's say we're combining a bunch of different molecules together to produce one singular molecule. A good way to make sure that even more of that molecule is produced is if we increase the pressure, well then all of these other molecules are going to be jostling around a bit more, and then we'll favor the side that produces the least amount of molecules. Increasing volume, same thing but in reverse. Increasing temperature will favor the side that consumes energy. So in an endothermic reaction, well, we consume energy in the forwards reaction, therefore we go forwards. And in an exothermic reaction, where we produce energy, therefore we want to take the endothermic version, which is backwards. All right, so for example, I'm just going to annotate this in. Here is a chemical equation. So nitrogen gas plus oxygen gas becomes nitrous oxide. There should be a 2 there, I believe. 2, yes, and that should be a 4. I do apologize. That's my mistake. Oh no, sorry, my bad. There should be a 2 just there. I do apologize about that. And that shouldn't be like, no, my bad. Sorry, I just messed this equation up. There should not be a 2 there. I do apologize about that one. Okay, so it's just NO. So we start off with a lot of products, so a lot of reactants. So I'm just going to draw in green our rate of reaction of our forward reaction. So we start off with a really high rate of reaction because they're the only chemicals around. But as we consume more and more of them, our rate of reaction slows down because there's less and less chemicals. Likewise, when we look at the backwards reaction, well, to begin with, we start off with no products, so nothing can happen. But as we add more and more products, well, slowly it's going to be going back and forth up until a point where the rate of forwards reaction equals the rate of backwards reaction, and that there is identical and that means that we have reached equilibrium. So if we begin with, let's say we have a ton of nitrogen gas to begin with, and that's slowly going to decrease. This here is our concentration. We have a ton of oxygen gas, and that slowly decreases in ratio. But as you can see, again in ratio, but we're producing two, for every one oxygen we're consuming, we're producing 2 nitrous oxide. That's going to slowly increase up until we reach equilibrium at that point. Let's say, for example, then we suddenly remove a lot of our nitrous oxide. Well, that's slowly going to decrease again. Increase again. And this here is slowly going to decrease again, and this one here is also slowly going to decrease again until at this point here they've reached equilibrium. So that's how it sort of happens. That's how it sort of occurs. And one of the common questions they ask is they try to get you to draw a graph. All right. So speaking of one of those questions, I will actually do one of those in a second. Just so for context, in industry, we also want to maximize speed and also maximize the product created. So an issue here is that in an exothermic reaction, we increase temperature to increase the rate of reaction, but increased temperature drives reaction backwards. So we hence got to try to find a balance between. Okay. We have a question here. So we have, this is where we're going to use an ice table. So we have 2HI becomes H2 plus I2, and 4 mole of the reactant, so HI, was reacted in a 2-liter vessel. When equilibrium was attained, 25% of the HI molecules are dissociated. Find the equilibrium constant. Okay. This is where we set up an ice table. Ice, so I initial, C change, E equilibrium. Okay, we start off with 4 moles of the reactant. All right. So we begin that initial 4 moles. We have no hydrogen gas, no iodine gas. 25% of the HI molecules are dissociated by equilibrium. Therefore, we're left with 75%, which is 3. Therefore, first things first is we've lost 1 mole of HI. Well, for every 1 mole of HI we lose, we're going to be losing half. We're going to be producing half of that in terms of H2 and half of I2. Therefore, we're going to be, and that's just the ratio of molar numbers. You can see for every 1 hydrogen gas, we need 2 moles of HI. Therefore, we're going to increase plus 0.5, so increase half a mole of hydrogen gas and half a mole of iodine gas. Therefore, our equilibrium is 0.5 and 0.5 for both of those. So for our concentration of HI is 3 on 2, so for 2 liters, so 3 mole and 2 liters, 1.5 molar. H2 is 0.25 and I2 is 0.25. The thing you got to carefully look out for here is the volume of the vessel. All right, therefore we're going to put it into a KEQ equation, and the thing to note here is that so there's 1 mole there, 1 molar there, 1 molar there, and then this is to the power of 2. Therefore, our 1 times 1 divided by 2 gives us m to the power of 0, which so means we don't have to put a unit there. I would always just put m to the power of 0. M to the power of 0 equals 1, so that's either or. But therefore, our total KEQ value is 0.028. All right, here's another quick question, and I've just received a question about competitive equilibria, which I'm actually going to explain in a second, so don't stress. Here's a question from the 2017 exam. So here we have a energy profile of an enzyme catalyzed reaction. Each stage of reaction is labeled. M is initial, N is stable intermediate, and P is final products. So which of these is the correct answer? So let's go through. Energy change from M to N is exothermic. Well, when we have one of these graphs, exothermic is where we lose total energy of the products is less than the total energy of the reactants, because energy is being released into the system. So therefore we know it can't be A. Energy change from M to P is exothermic, or M to P is also increased, so that can't be true. M to N is endothermic. Well, that could be true. M to N is endothermic. We have to put energy in. We have to put energy in to reach that. Energy change from N to P is endothermic. Well, no, that energy change there is exothermic. Finally, well, we know it's got to be D, but the energy change from M to N is endothermic. Yep. And M to P is endothermic. Yep. So the careful distinction there is C is N to P and D is M to P, which is why it pays to use your reading time to read all of this stuff. And that there is our answer, D. Okay, I'm just going to do a quick run through this equilibrium question before we move on to our Q&A, a bit of a break. A student investigates the following reaction where a reactant gas is brown and product is colorless. A reaction can be observed in a sealed test tube. State the color change expected when the student places a sealed test tube in a beaker of hot water and explain why this change occurs. So 2NO2 becomes N2O4, and then we have an exothermic reaction. Okay, as the forward reaction is exothermic, the backwards reaction is favored at higher temperatures. Therefore, in this beaker of hot water, we're going to be favoring the backwards reaction, producing a greater concentration of NO2. NO2 is brown, and then N2O4 is colorless. Therefore, at equilibrium, when we put it in this hot water, the equilibrium mixture is darker in the hot water than it would be at room temperature. Therefore, the color changes to a dark shade of brown. That's how we answer that one. Okay, the graph below describes concentration versus time at 22 degrees Celsius. Calculate EQ at T1. So T1 is where they've reached equilibrium. At T2, the volume of the system is halved. Continue this graph to show how this change would affect the equilibrium and how the system would respond to this change. Okay, well, to calculate it out, all we're going to have to do is look at our concentrations. N2O4 at T1 is 1.5 by 10 to the negative 2. You've got to look out for that one. This here isn't just 1.5. It's measured in 10 by 10 to negative 2 molarity. NO2 is 5, then times by 10 to negative 2. And all we're going to do is simply put that in our equation there, which gives us 6.0 molarity to the power of negative 1. Okay, part C tells us that at T2 our volume is halved. Classic trick here is people then half the concentration on the graph. That's not true. We actually have to double the concentration if volume is halved. Therefore, from 1.5, we're going to jump up to 3. That's where we jump up to. And then we're going to jump from 5 all the way up to 10 there. So reaction favors the side that produces the least amount of particles because our volume has been halved. Least amount of particles is a forward reaction. Therefore, we're going to be slowly decreasing amount of products and increasing amount of, decreasing amount of reactants, increasing amount of products. That's essentially what it would look like. That's all you need to do. Okay, awesome. Just a last little thing on competitive equilibria. This is a fascinating one, which is a real world example, but we have in our bodies, hemoglobin, which is in our blood. It's like in our blood cells. It binds to oxygen to carry it around the body. So HB, hemoglobin, plus O2 becomes HbO2, simple enough. But hemoglobin can bind to other gases. The main one here is carbon monoxide, CO. Hb plus CO becomes HbCO. Now K2 is much stronger, and hemoglobin much more, really loves to bind to carbon monoxide. The reason why is because, when we have our blood, in our blood, we breathe in oxygen, our blood picks up the oxygen, then has to go drop it off somewhere else. So the equilibrium constant has to be enough for our hemoglobin to pick up oxygen, but also drop it off around the body. But we don't need to, there is no function of carbon monoxide in our body. So carbon monoxide just binds really strongly and we kind of can't get it off. And then that's really toxic because it means our hemoglobin is taken up and means we can't actually get any oxygen transport around our body. And even at low doses, it's quite toxic, which is why, historically, there's been lots of cases of babies dying, for example, left in a room where a radiator hasn't worked well because the carbon monoxide levels are too high. So what happens is we place a patient in a hyperbaric chamber with pressurized oxygen. So this, because in the air, there's actually not that much oxygen. So we place them in an environment with a lot of oxygen. So our O2 dramatically increases. What happens is when we increase a reactant, we're going to drive this reaction forward. Here, because we're driving it forward and we've got the same amount of hemoglobin, we're decreasing the hemoglobin here. Well, now in this reaction, this bottom reaction, K2, we're decreasing hemoglobin. Because we're decreasing hemoglobin, the reaction is pulled that way, which separates our hemoglobin from the carbon monoxide. That's how competitive equilibria works. Awesome. Okay. We're going to take a quick break. There's just a couple of videos from UBS that I'll just show. And then we'll do a quick Q&A session for you guys to catch up. After these videos, feel free to go and grab a coffee or whatever. All right, we'll just watch these in the meantime. I just need to make sure I'm sharing sound. Check the video sound.
Hi, my name is Michael Bevilacqua. I'm an analyst within the consumer products and retail team at UBS. I ended up at UBS after studying a double degree of commerce and law. And the two subjects that I probably enjoyed most while I was at school in Year 12 were two that I actually didn't end up pursuing at all later on in life, which were literature and chemistry. Knowing what I know now, I would say that certainly while your VCE score is important and you should give it all that you've got, it's not going to define your life, and you certainly won't be defined by a number if things don't turn out well in the end. There are unconventional ways to get into different courses and different things later on in life. So I would say certainly give it all you've got, but don't be overcome with stress during this period. Hi, my name is Michael.
Hello, Skyline students. I'm Jamin, and I work in the investment bank technology sector at UBS. My work involves software programming and helping with business analysis. So I studied in New South Wales for the HSC about 2 years ago, and I enjoy taking maths, English, chemistry, and physics. There weren't any specific subjects which led me to my role. Rather, none of my subjects were economics or business related. And so, my advice to my Year 12 self would be to make sure to eat well and sleep well, and make sure to keep that diet nutritious, because in my HSC period, I was mostly at home and had to be responsible for my own food. And lastly, best of luck. Thank you.
Absolutely fantastic advice, guys. So we're going to just run a quick Q&A session. Feel free to take a break. We'll set up if anyone's shooting questions through, we'll just set up the Q&A thing right now. Feel free to grab some water, go to the bathroom, whatever you guys need to do. We're going to be studying again at maybe 3:15. I'm just going to, set that up. Excuse me. Here. Awesome. Okay. Can everyone see that one? Michael, jump in. Feel free to answer any of these questions. And students, feel free to direct any of these questions towards our awesome volunteers. I do just have a question in the chat. How many practice exams do I do in total? Now that's a really rough question. I want to warn you that there is such thing as over preparing. So for methods, for example, I did maybe 50 practice exams of exam 1 and exam 2, so 100 in total. That was a ridiculous amount. I would have done the exact same if I did maybe 30 in total. There is an amount that you need to do, for sure, in order to get that exposure to those questions, especially in a math subject or a science subject, but there is such thing as too many. I would recommend, I think for every person is different, I recommend keep doing exams until you feel confident enough. And when you're not seeing a change, and if you're doing 10 exams and you don't see a change, like you're doing well each time, well then practice something else. Awesome. Now, volunteers, would you guys like to take some of these questions? If you guys can remember all the way back to your Year 12 experiences.
I took a pretty unconventional approach. So I never went to bed anywhere near as late as a lot of my my friends. A lot of people used to study for 4 or 5 hours a night, but it was pretty unproductive study. I found that I'd rather get home, do kind of three odd hours, but do 3 odd hours of actually productive study and then go do something else with the rest of the time. I found that I was just far more productive that way.
Yeah, I think that's a really good point. There is studying isn't a goal to see how much you can do. It's the content you do. So sitting there and you're spending 5 hours and doing like 1 hour's worth of content isn't anywhere near as good as spending 1 hour doing the same amount of content, because then you've got all the other time. I think the important thing, especially for everyone here, you're in lockdown, the last few weeks of school, it's really important to keep your like mental health up and make sure you're doing things you enjoy as well. Fantastic question. Is it hard to obtain scores of around 40 if you haven't done well on SACs? Yes, it is. Okay, so this is a classic question because the way VC is run is that they don't look at your score and say, oh, you've only got like 20 out of 40. They look at how well your cohort does. So because obviously you don't have the same SAC in your school as other schools do, and it'd be very unfair if people who just had easy SACs did better in VCE. The main determinant of your study score is the exam, and the exam to some degree affects the score you get for your SACs, because your SACs are just a ranking. So yeah, I'll tell you a story there. One of my best mates is doing medicine with me, and he wasn't a very hard studier throughout year 12, but he decided in the last few weeks, or the last couple of months rather, to really study hard. He was doing PE. This is when he was doing PE 3, 4 in year 11. And he was ranked maybe 13th or 14th in the class, like about halfway, not fantastic, not awful either. But he ended up studying really, really hard and did very well on the exam. He did very well on the exam to the point where I don't think he got anything wrong on the exam. Now, that's obviously a huge example, but he went from being ranked 13th or 14th in his class and ended up getting a raw 50. So ultimately, now that's a very extreme example, but ultimately what matters most is your exam scores. Yeah, exactly how what I was talking about. Yeah, so when your SAC scores increase, so all your school does is they're not looking at like how you got 25 out of 40, 25 out of 50 or whatever. For each of your cohorts, each of your classes, you get ranked. So you get like if there's 20 people in your class, you get ranked 1 to 20. And if your rank 1 does well in the exam, then their SAC score as a rank 1 will become their exam score. Their exam score becomes their SAC score. So you could be rank 1 and then you get a 40% on the exam, or then you can get 40% for your SACs in total. If you get 90% on the exam, you can get 90% of your SACs. So all that matters is your exam score essentially. And what's really good about VCE, I think, is that when it comes to exam scores, is that you actually benefit from working with the people who you're in your class with. That's a really important note, I think. Sorry, volunteers, feel free to chip in at any point. Go for it. Okay, Unit 3, Unit 4 this year, because Unit 4 is smaller, as we're going to run over with like food chem, there's going to be less of it on the exam, I'd imagine. That doesn't mean you should study it any less, because again, I don't write the exams. We don't know what the exam looks like until you go on the exam. But there is usually heavy emphasis on organic chemistry, and less emphasis on food chemistry anyway. Awesome question. Volunteers, do you have any thoughts on like doing multiple choice or short answer first?
So for me, I start off with multiple choice because I want to get it out of the way as fast as I can. And the marks are more discrete. So it's probably, for me, it's a good idea to get it out of the way. And then if I can't do it, I'll mark it and come back to it.
I've always typically taken, and this just goes to show you that it's a matter of personal preference, I've taken a different approach where I've gone straight to section B. I've just found that given there's generally more marks per question, if I can get a few runs on the board there, it's probably a better allocation of my time as opposed to, say, multiple choice questions, which may be worth less.
Yeah, I think those are both absolutely fantastic points. And what it comes down to, yeah, it is a matter of personal preference. So when you do practice exams, practice some of them with doing multiple choice first and then do short answer, and then practice some doing short answer and multiple choice and just see what you find to be better for you. Okay, we'll go through the content or just jump straight. Okay, if you're not confident with content, again, going back to the start, what I talked about, your skills, textbooks, I reckon, in my opinion. And as soon as you think you're ready for exams, do exam questions. You don't even have to do a full exam. Just take exam questions from online, or like from the online exams, or from this books that compile exam questions, because ultimately, like the biggest determinator of how well you're going to do in the exam is your exposure to exam questions. So it's important to do the exam questions, but it's a waste of time if you're doing them without any knowledge or background. Oh, other subjects like English. Volunteers feel free. Michael, you said you enjoyed this show a lot in high school. Do you want to talk a bit about that?
Oh, it was 8 years ago, so I'm not sure I really remember how best I prepared. I might have to defer to your judgment, given you're only a couple of years out from that one.
Yeah, very fair. Yeah, go for it.
Yeah, so preparing for English, I'm not sure how your English exams are structured, but we had section A and B, where we had to prepare several essays. So one essay and one creative for section A, and there was a reading section, and then section B we had to prepare three essays. And wait, what's the English situation like in Victoria?
Very similar.
So for the reading section, definitely doing practice, any sort of practice. So you would try and get a text and try and summarize it, or even if you have get past papers, definitely. And then for English, how I prepared was I made sure to have a solid essay which I could fall back on and adapt to the question and adapt it to many different types of questions and try and also definitely I got a lot of help from my English teacher, and it's definitely a good idea to get feedback from not just your English teacher but from your peers as well, and you can do peer marking and so on and give each other feedback, and that's how you can better improve your English skills.
Absolutely fantastic advice. Thank you so much. No. Okay. So if your classes will do on the exam, it affects me too. No. Okay. So that's also a common misconception. I probably didn't explain it well. If you're essentially, the way I would look at it is if all of your class does very well, you're more likely to do well. So your class can bring you up, but they can't necessarily pull you down. Essentially, the biggest determinator of your study score is your exam score. And that is usually only like if your cohort does well or boost it, but if they don't do well, typically there won't be much of an effect, or if any. So don't stress at all about that one. The right state. Yeah, so state okay, so what I'd recommend doing is when you go through a question, highlight all the key terms. Go through and if they say like aqueous, zinc, or aqueous copper, like ions. If they say ions, it's usually aqueous. If they say like melted or liquefied, even if it's metal, it's going to be a liquid. Or if they mention solid, obviously put that down. Worst comes to worst, put down solid for your metals and aqueous for everything else. And you might not get the marks, but it's much better than to write something like that down and potentially get it wrong than not put anything and definitely get it wrong. I think that's the whole idea. As in medicine, does it focus on chemistry or biology? I think with any university degree, and I'm sure the other volunteers could agree with me on this one, is that they're not so clear cut. Like it's not like a high school where you just do chemistry or anything like that. Like for med, like sure, there's a lot of chemistry. It talks about physiology, a lot of biology, obviously in terms of like human body, but we also do a lot of arts, a lot of essays. We've got to write about medical, like for me, I've got to write about medical law, got to write about medical ethics, got to write about health promotion, like how we hospitals work and that sort of stuff. So in uni, it's much less clear cut than it is in high school. I don't know if anyone else wants to add into what I've just said.
Yeah, I'm doing computer science right now, and it doesn't just focus on coding or programming, because we have to do maths courses as well, and so they give you a quite well-rounded education as well in uni.
Yeah, definitely.
Yeah, I find you'll probably learn what you've learned in a whole year of VCE within a few weeks at uni. They'll just give you a much more compressed version of certain topics, which does give you that broader range.
Yeah, 100%. I think that's a really important key point, is that though VC sounds really hard, but like in uni, like we go through it like so quick. Like I didn't do biology in high school, and I essentially learned all of the bio 3-4 course within my first few weeks at uni, just to catch me up to speed. Like that's the university was teaching that. I'd bring us all up to speed. So yeah, that's awesome point. Do you feel I got a better or worse? Now I think expectation is a dangerous thing, but I think personally, there was like study scores I hoped for and study scores I expected. Like obviously, like I'd hoped for a 50 and I didn't get a 50. But I also expected, like on the day, I sat there thinking about how well I'd done. And I made quite a few mistakes on questions. I actually thought I got a much better study score than I expected. Ultimately, like you don't know, because your study score isn't like a score on the exam. Your study score is based on how well you do compared to everyone else in the state. And 1 year, 100% on the exam could get you a perfect score, but the next, it might not. So I think expectation of study scores is a very dangerous thing. Did we get 8 hours of sleep? Go for it.
I did. Like I mentioned, I actually found that getting sleep put me in a better position. If it meant sacrificing some time from study to get a better sleep, I'd pay attention a lot more in class, which, I'd make up that hour incrementally. So I definitely tried to, and I found that practice worked better for me, but I also found that I needed more sleep than other people.
We might just answer one more question. Oh, sorry, I might just answer one more question and then we'll head back to content. Then we can do a bit more Q&A at the end. Just want to make sure we cover everything today. So how do I study for the exam? Do I start studying for just chapter 1? Yeah. So if you forgot something in unit 3, that's fine. Yeah, definitely use your textbook, but I wouldn't recommend maybe go through, reread your notes, but questions are the best way to study for a subject like chemistry, in my opinion. Like there's no point just sitting there rewriting notes, because chemistry is much more of a subject of application than it is of memory. And the memory stuff you have to learn is you definitely flashcards or whatever, but it's more like you're going to memorize it much better if you know how to apply it as compared to know just what everything means. Alrighty. We are going to head back to our PowerPoint. Just give me 1 second. Okay, so there's quite a lot to cover, so I apologize if I brush over things quite quickly, but I shouldn't. We've got more than enough time. From current slide, okay. Organic chem pathways and fuels. Okay, so we have a range of functional groups. Now, the thing to note is that they may talk a bit about amides in the exam, but technically amides are here, as we can see, it's a double bond oxygen with NH2. It definitely can come up, but we don't need to worry about ourselves about it as much. Carboxylic acids and esters, well, we rank different functional groups in importance, and in VCE, carboxylic acids and esters are our most important functional groups. Aldehydes are next, then ketones, then alcohols, then amines. So when we're naming a molecule, this is pretty basic stuff, but double, triple bonds are combined in the name, and halogens never take priority. So when we have an alcohol, for example, we're going to call it, say, butanol. And we have a carboxylic acid, you might call it butanoic acid. Because carboxylic acids are more important, if we have a carboxylic acid that also has an alcohol group on it, well, alcohol is less important. So we're going to, instead of calling it butanol, we'd call it like 1-hydroxybutanoic acid. So the prefix, we keep the prefix of the most important thing. Sorry, the suffix of the most important thing, the ionoic acid, and the prefix like hydroxy for alcohols is given if it's less important than other ones there. Halogens like chlorine or bromine never take priority. So it will always be chloro butane or bromoethane. So essentially, what we're going to do when we see a molecule is we want to identify functional groups and branches, and there should never be more than 3. At the most, you might be expecting to see 2 functional groups and 1 branch. Identify the length of the longest chain. Well, so the longest chain, so the longest consecutive lots of carbon molecules is our parent molecule, essentially. And if there's 5 of them, well, then we're going to be having we're going to call it pent. If there's 4, it's bute. 7 hept, etc., etc. So we name our molecule after the longest chain. We add our priority suffix and then our prefix attached to the number of carbons. So let's say we've got a 5 long carbon chain. It's got a carboxylic acid essentially, so a carboxyl group on the end, and we've got alcohol on the second carbon from the end. Well, then we're going to say it is 2-hydroxy pentanoic acid. Then we add the names of the alkyl branches, so add the names of the branches in before. And if there's more than 1 group, we use di, tri, or tetra. So classic example here is if we've got 2 chlorine atoms on the end of the molecule, so carbon number 5, we might call it di-5,5-chloro 2-hydroxy pentanoic acid. Bit complicated, but definitely not something we're going to cover too much in a lecture format. But if you're unsure about that sort of stuff, definitely give it a practice. Okay, there's different types of bonds between molecules, and this determines something like boiling point and melting point, those sort of things. So we have intramolecular bonds, which are the bonds between atoms inside a molecule, and intermolecular bonds, so between molecules. So these include ionic bonds. This is intramolecular bonds, so ionic bonds, metallic bonds, covalent bonds. So they're just a type of bonds between atoms inside a molecule. So covalent bonds is something to especially touch on. That's where we share an electron between two atoms. But the more electronegative an atom is, the more of the electron's time it will take up, essentially. Where it gets to the point where the electronegativity difference between 2 atoms, like sodium and chloride, is so great that the sodium actually just donates its electron to the chloride. In a carbon-hydrogen bond, the carbon is more electronegative, and therefore it gets the electron a bit more of the time than the hydrogen atom. Therefore, we say, because electrons are negative, that carbon is slightly negative and hydrogen is slightly positive when they're bonded together. Use of intermolecular bonds, and they're like dipole-dipole interactions, so where we have a charge on one end of a molecule interacting with a positive charge on the other end of a molecule. Hydrogen bonds are where we have a hydrogen that has to be bonded to usually an oxygen, interacts with another oxygen or a nitrogen, which is a dipole-dipole interaction, but much stronger. And dispersion forces. So dispersion forces are the forces created between slightly positive hydrogen atoms connected to carbon, and when they brush up against, say, a hydrogen connected to a carbon that's slightly positive just for that, slightly negative just for that moment in time. Don't really need to know much about like the intricacies of dispersion forces, but essentially they are very weak, but they exist between hydrogen molecules, hydrogen atoms of adjacent molecules. Okay, so physical properties of organic molecules will follow a pattern based on strength of molecular bonding. So hydrocarbons are the weakest. They've usually got no oxygen, well, they have no oxygens or nitrogens or anything. Esters, aldehydes, ketones, and amines usually have an oxygen involved with them or a nitrogen. They're all roughly similar. Like, it's going to be very hard to differentiate between the boiling points or the physical properties of an aldehyde or a ketone, but they're much less stronger than 2 alcohols joined together, and which are much less stronger than 2 carboxylic acids, because alcohols have an OH, which can form a very potent dipole-dipole interaction, and carboxylic acids can form hydrogen bonds. So because a greater amount of energy is required to separate carboxylic acid molecules from adjacent carboxylic acid molecules from each other, they're going to have the highest melting point and boiling point, highest density, highest viscosity, highest flash point, and lowest volatility. All right, just some basic pathway reactions. We have substitution and addition. So substitution is where we have a hydrocarbon and one halogen atom. So in the halogen line of the periodic table, replaces or is substituted for a hydrogen atom. So to do this, we require UV light and heat. Reactants are an organic compound and halogen gas, and we swap out, one hydrogen atom, it should be hydrogen or halogen there, I apologize, for chlorine. But this can produce different isomers. So for example, we have CH3, CH2, CH3, so propane there, we add Cl2, we're gonna get HCl, and we could get Cl on the terminal carbon, or we could get Cl right in the middle. And this is what that terminal carbon would look like, but if we added that chlorine on, but that chlorine, that could actually be an H there, and we could have the chlorine down here, just as an example. All right, that's different to an addition reaction. And in an addition reaction, we have a carbon-carbon double bond in an alkene. An alkene is where we have a double bond between two carbon molecules. And atoms are added to the molecule. That's why it's an addition reaction. So we can do various things here. We can add water, so H2O, which separates into H and OH, to make an alcohol. Very expensive process because it needs to be very hot and requires an acid. We could add hydrogen gas, which we don't really need much for. We can just put hydrogen gas in and it forms a saturated alkane, which means there are no double bonds involved. If we add a halogen, we form a dihalogen alkane. That requires a catalyst, but we can also create polymers. So we can add separate ethane molecules together, for example, which is how we make plastics in industry. So here's an example. We have ethene, we add bromine, and this double bond here almost snaps. Because there's a lot of electrons there, this bromine will come here, and one Br molecule will end up on the first carbon, one will end up on the second. Awesome, okay. Oxidation reactions are the next one. So alcohols can be oxidized by strong oxidants to produce aldehydes or carboxylic acids. The strong oxidants you need to know in VCE are permanganate, acidified permanganate, which is NMO4 negative, and H plus for acidified, and acidified dichromate. Dichromate, if you remember, right from the start of redox, this is something I was talking about, which is Cr2O7 negative. Now, interestingly, we have distinctions of primary, secondary, and tertiary alcohols. Now, this essentially relates to the number of carbons bonded to the carbon bonded to the OH. So primary alcohol is where the OH group is on the very last carbon of the molecule. As you can see, there's only one carbon attached to it, which means it's at the end of a chain, at the end of the chain there. A secondary alcohol is where we have, say, a carbon, 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 and our OH group, as you can see, is bonded to that middle one. Tertiary is a bit different. That's where we might have a branch as well. So there are 3 carbon molecules bonded to the carbon atom that the OH is bonded to. They're the difference, essentially. All you need to know is a primary alcohol, a ketone and an aldehyde will differ. They're both where we have a carbon double bonded to an oxygen. Ketone is where it's in the middle carbon atoms, and aldehyde is where it's at the end. And we can only produce a carboxylic acid if we have a primary alcohol to begin with. This is what we look like. So essentially, when we have this, here we've used CrO4. We don't need to know that one for VCE. Here we have a primary alcohol. So this is the end of a chain. That's going to become a carboxylic acid when oxidized. A secondary, where we have the OH in the middle of a chain, that's going to become a ketone. The other thing you have to know is that if an aldehyde will also become a carboxylic acid. Technically, in real life, what will happen is we will oxidize a primary alcohol to become an aldehyde, which will then become a carboxylic acid. In VCE, we don't need to know that as much. But essentially, oxidation is essential for swapping the OH for a C double bond O. In VCE, you just need to understand that primary alcohol will become a carboxylic acid in the presence of oxidizing agent and heat. Okay, condensation reactions occur when there's 2 different functional groups which link together to form a compound that produces water. Condensation, like when you're in the shower and water appears on the mirror, because you're producing water essentially. Here we have a alcohol and a carboxylic acid to create an ester. The H of the hydroxyl of one of the molecules and the OH of the hydroxyl of the other join together, or they break off, that joins the 2 molecules together, and that becomes a water plus an ester. Esters are formed between carboxyl and hydroxyl groups. Ethers, which are like esters except you don't have that double bond O, They're formed between two hydroxyl groups. So there's just an O joining different carbon molecules. And amides are formed between amine and hydroxyl groups. So they'll take the hydrogen of the amine group and add it onto the OH, which separates to become water. All right, hydrolysis is the exact same thing in reverse, essentially. It's where we're losing water, hydrolysis. So reactant plus water becomes the product. So if we add water to an ester, we're going to separate it back into the carboxylic acid and the alcohol. All right, here is a classic question from an exam. So this is, I've done this one myself, but it's based very much on exam style questions. We have a pathway and we're producing butyl propanoate. We're starting with 1-chlorobutane and propan 1-ol. So what I'd love for you guys to do, I'll give you maybe 5 or 6 minutes. Try name and draw the structures of product X and Y, draw the skeletal formula of butyl propanoate and give that a go. I'm just gonna give you guys like maybe 5 minutes to do this, see how far you can get. All right, absolutely fantastic work, everyone. This is a long question, so do not expect for a second to have it done in 5 minutes. But essentially, this is a sort of question that VCAL love to throw at you. Pathways are a really important thing chemically, and as you can tell, the theme sort of this study design is more like industrial based, and this is like what we'd actually have to do, go through so many different steps and stuff to produce esters. Now, I don't know if you've ever seen an ester or produced it in a lab at school potentially, but they're actually very, very cool. They often smell very fruity and they just are very interesting. So we're ending up with butyl propanoate, and we have 1-chlorobutane and propan 1-ol to begin with. Okay, so let's go through our questions. All right, part A is name and draw structures of product X and Y. Well, we're producing butyl propanoate. Now, if you guys remember, way back to, probably a couple months ago, for you guys now, anything ending with il and then OH is an ester. An ester requires carboxylic acid and an alcohol. All right. Alcohols can be produced by substitution and addition, and acids from oxidation by alcohols. All right. So you can see here we have 1-chlorobutane goes to product X, propan 1-ol goes to product Y. The classic stitch up here is saying, well, we've got an alcohol here, propan 1-ol. Let's make chlorobutane into an acid. Well, no, we've got butyl propanoate. Butyl refers to the acid, the alcohol. Therefore, we need a 4-carbon long alcohol, and then propanoate refers to the carboxylic acid. Therefore, we need propanoic acid. Therefore, chlorobutane has to become an alcohol, and propan 1-ol has to become an acid. All right. Here is my very poor drawing of 1-chlorobutane. We have a chlorine atom on the first carbon, and we need to somehow swap it to becoming butane 1-ol. Okay, how do we do this? So product X, butane 1-ol. Awesome. Then product Y, we're swapping, and oh, that's my bad there. I need to change these. I apologize. When we oxidize, we get rid of one of the carbons, so one of the hydrogens. So we replace that with an OH. Sorry, with a double bond O. And so product Y, therefore, is propanoic acid. All right, okay. Draw the skeletal formula for butyl propanoate. Now, this is a classic question. They're likely to ask you this year. Skeletal formulas are very tough, though. They might be very new to you, actually. How do we draw skeletal formulas? Okay, well, I'm gonna draw some for you now. But essentially what we do is we draw a line, and that line represents bonds between two carbons. So there's a carbon here and a carbon here. If we draw another point, another line, well, that bend, that point there is one carbon, and the end of each of these is another carbon. So for butyl propanoate, we need 4 carbons. So 1, 2, 3 is our third, and then sorry, my bad. Then this here is our 4th carbon. But to join on to an oxygen, well, we have to write in the oxygen. So we make sure that point represents a carbon. And then instead of continuing all the way, we're just going to draw in an oxygen. Likewise, we now have to do propanoate. So, okay, well, here propanoate is a propanoic acid. So we have 3 carbons. There's our first carbon here, that point there. There's our second at that point, and our third is at the end there. to draw a double bond O, we just draw it right off the point because double bond O comes off of the carbon. That there is how we draw a skeletal formula, and that's all the detail you need. But that there would give you a couple of marks on the exam. Super important, like definitely if you're stuck on those sort of questions, lots of resources available online that I really encourage you to look out for. Because this is the first year where they explicitly mention skeletal formula in the study design, your textbook might not actually cover it, which is why the internet is such a valuable resource in terms of chemistry study. All right, okay. Our next question here is, write the chemical formula for appropriate substances to use region A and region B. Okay, region A helps our 1-chlorobutane become our alcohol. So region A is involved in a substitution reaction where the chlorine is replaced with hydroxide. We get rid of chlorine, we put in hydroxide. So therefore, there's got to be a hydroxide salt. So it's got to have like NaOH, for example, or KOH. They're classic ones because they're the OH and the metal will really easily separate, and then the chlorine will jump on and almost like a bond with that metal as well, and then the OH will jump onto the metal, sorry, onto the element, onto the molecule. Region B is involved in oxidation reaction of a primary alcohol to a carboxylic acid. Therefore, B must be a strong oxidant. You could have said acidified dichromate or acidified permanganate. Okay. Write the chemical formula for an inorganic compound formed at the same time as organic product X. Okay, this here is where it's a bit tricky and depends on your answer. So let's say you said your region A was NaOH. Well, then we'd have like this. We'd have this happen. So our OH jumps onto the molecule, and then our chlorine goes with the Na. If that was KOH, so here's our answer. NaCl is the inorganic salt. If you used KOH in the last answer or anything else, you'd have KCl. So this is a question that very much depends on your last answer. Now, finally, describe the difference in boiling point between propan 1-ol and a product Y. Well, let's go through this. Okay. Product Y is propanoic acid. Propanol can form dipole-dipole interactions between the hydroxyl group and hydrogen atoms. But propanoic acid can also form hydrogen bonds between the hydrogen of the hydroxyl group and the oxygen of the carbonyl group. That's the C double bond O. Hydrogen bonds are stronger than dipole-dipole interactions, hence more energy is required to separate adjacent molecules, meaning product Y has a higher boiling point than propan 1-ol. Just a bit of a throwback, just something to consider when you're answering these sort of questions or looking at questions. Choose questions that integrate as much of the course as possible. All right. Now, there are various different types of analysis. Chromatography, volumetric, IR spectroscopy, and NMR spectroscopy are the big ones in VCE Chem. Now, today I'm not actually going to cover much on chromatography at all. Chromatography is fairly straightforward, and I think you guys would benefit much more from, instead of me just going through a question and showing you, you'd benefit much more from, if you're unsure about it, doing a bit more study. But that is not an important part of the VCE course. The most important parts are spectroscopy when it comes to analysis. There will always be a spectroscopy question on the exam, especially now they've removed mass spectroscopy from the study design just for this year. There's definitely going to be a short answer question on IR and NMR spectroscopy. Volumetric analysis is redox and acid-base titrations. Redox titrations, again, aren't that big in the exam. You're very unlikely to see it. But acid-base titrations will appear every single year, and it will usually focus on experimental error. And experimental error is something they love to assess in VCE. All right, let's jump in. Okay, titration we'll begin with. Titration, there's a lot of key words to remember, but essentially we have a burette that's clamped. Down the bottom is a volumetric flask or an Erlenmeyer flask. Usually we call it volumetric, and titer. So the titer is the volume of solution that goes from the burette, this big cylinder here that goes into there, and the aliquot is the amount of solution measured by pipette, which is the aliquot is usually this solution there, the volume of that solution there. Okay, a pipette is used to measure an aliquot, which and I ignore that next bit, but that's put into a conical flask. We then put an acid-base indicator, and a titer is added drop by drop until the solution in the flask permanently changes color. Okay, so what's actually happening here? Now, usually we will put into this into the flask a known substance with an unknown concentration. We're going to try to figure out how concentrated it is, and we're adding either we have an acid in the titer in the burette and a base in the volumetric flask, or vice versa, and you can calculate concentration by through stoichiometry. So you figure out how much acid is needed, for example, in order for the solution to become neutral. And the reason why it changes color is because we have an indicator, and the indicator will detect when the solution becomes neutral and then change color. Yeah, that's the basics of it. But it could be the other way around. We could, for example, have an unknown concentration in the burette and have a known concentration and volume in the flask. But, you know, I don't really see that happening as often from my experience with chemistry questions. Usually, we can't just have one experiment and say, yep, we can figure it out. Because the whole thing is, one drop of a titer will change the color of the volumetric flask. So you can add just a little bit too much, and then you shifted the pH way massively. You remember pH is incredibly delicate, and this is an acid-base titration. Because you've shifted the pH massively by adding one extra drop, we usually do this at least 3 times. And we need to get measurements that are within 0.05 milliliters of each other. And if they're not, well, then we do it again until we keep doing it until we've got at least 3 concordant titers. So 3 titers that are within 0.05 milliliters of each other. Okay. Indicators and equivalence points versus the endpoints. Okay. So there's two different definitions here. Endpoint is where we see a color change, and endpoint signifies that we stop the titration. We stop dripping titer in. It's the end. The equivalence point is where the essentially where the acid or the base has been neutralized. Essentially. And so ideally we'd have an equivalence point that is the same as the endpoint. But because we don't, different acids and bases will react to different pH levels, essentially, we need to use different indicators as endpoints may differ, that the pH of the endpoint may differ. The pH of the equivalence point may differ, and therefore we need to have indicators that represent the endpoint properly. Okay. For example, we have a hydrochloric acid and sodium hydroxide, very strong acid, very strong base. When you put them together, they will neutralize at a pH of 7. Therefore, we're going to be using, usually, an indicator that changes color around 7. Okay. I think it's here, yeah, so this acid here, H2CO3, is a very weak acid. NaOH is a very strong base. Therefore, when this is neutralized, this won't donate all of its protons. Therefore, it's going to neutralize at a very basic pH, a pH of 11. So we can't be using the same indicators for all of these. We might have to use an indicator like that's changes color at a much higher pH, because that's when the equivalence point is going to occur. Likewise with HCl, which is a strong acid, and then NH4OH, which is a very weak base. Well, that will have a pH of neutralization that's more acidic, so 5 or 6 usually. So therefore, we're going to need a different indicator for those sort of things. That's why there's so many different indicators. And this chart here is from your data booklet, if you haven't seen that. So if you see in a question, they use bromophenol blue, well, then you know that bromophenol blue has a color change from yellow to blue at a pH of 3.0 to 4.6. Therefore, you know that that's probably going to be a very strong acid with quite a weak base. Awesome, because the pH is so low. Okay, there are various sources of error. So we have our burette, which is that big long stand thing, our pipette. It contains the aliquot, which goes into the volumetric flask or the conical flask. But essentially what happens is if we wash it and we add some water left over, even a few droplets are going to dramatically change our values. So when we wash something, we should we wash it before we use it. This is a question that commonly comes up. You wash it with water, and then you make sure you rinse it with whatever acid or base is being titrated. That's going to be being put in there, just so you've gotten rid of all the water. The final rinse for the pipette should be with the solution it will contain, which is the aliquot, and because the water will dilute the solution concentration, even just to a small degree. And again, the conical flask should be rinsed with deionized water because the conical flask, because we know the concentration of what we're putting in the aliquot, so it kind of doesn't matter if it's a bit diluted in the conical flask. All right. Oh, and sorry, and rather just to add on to there, if the acid base from the pipette is not used, the acid base from the pipette should not be used in the conical flask because this will increase the number of moles present, and therefore the titer will be greater than it should be. And rinsing with the solution from the burette will cause some of the titer to react before the volume of the titer is recorded, meaning it will be lower. Essentially, this is just memory stuff. Practice these questions. Awesome. Okay, so analysis question. I'm going to take you guys through this. So a student determined the concentration of ethanoic acid in vinegar by the following method. Using a pipette, 25 milliliters of vinegar was added to 250 milliliter volumetric flask and water was further added. A 20 ml aliquot of 0.1152 NaOH was titrated against a vinegar solution from a burette. This was repeated 3 more times. Okay. What they're asking us to write down an equation for the reaction that occurs between sodium hydroxide and ethanoic acid, then calculate the molarity of the diluted vinegar, calculate the concentration, explain why the vinegar was diluted, and then which of the following should the burette have been rinsed with. Okay, let's give this a go. First off, write the equation for the reaction that occurs between NaOH and ethanoic acid. Simple enough. C2H3OOH. Is ethanoic acid plus NaOH. We're going to swap the H. The H is an acid, it's donated. We add on the Na, or you could have Na and the C2H3OO separate plus water. Amazing, because so essentially this hydrogen here is going to jump and then bond to that one there, and that sodium is going to bond to there instead, or it might dissociate from that bond. But like you can, this is how you can write it. Okay. Part B is calculate the molarity of the diluted vinegar solution. So this is a bit trickier. Okay. So if we go back, if you don't mind, you can see we have 4 different titers. These are all pretty similar. The only issue is this one here is 24.16, where the others are all 22. This is not concordant, and when we calculate in order to calculate stuff, we've got to use the average value, and we no longer include this value in the average because it's so different from all of the others. That's just something to know. So the average concordant titer is 22.86 milliliters. We're using 20 mils of 0.1152 sodium hydroxide. Therefore, we're going to be using a bit of stoichiometry. So if we remember our equations, number of moles equals concentration times by volume. Number of moles of NaOH equals 0.1152 molarity times by, molarity is moles per litre, so we've got to put the milliliters into litres, 0.02 litres, which gives us 0.02304 moles of NaOH. If we look back at this equation at the top, for every 1 mole of NaOH, we only need 1 mole of ethanoic acid. So the number of moles of ethanoic acid is the same as the number of moles of NaOH. Awesome. Okay. The concentration of ethanoic acid is number of moles divided by volume. Concentration is moles per litre. Therefore, it makes sense that if you have the moles divided by the amount of litres, you're going to get our actual value. Number of moles, as we know, is 0.002304, and the average concordant titer was 22.86 milliliters, or 0.02286 litres, which gives us 0.1016 moles per litre. Therefore, the concentration of ethanoic acid in the diluted vinegar solution is 0.1016 molarity. And then, yeah, that's exactly what I was talking about right at the start. You have to cross out that 24 milliliters because it's not concordant. That's the key term there, concordant. All right. See, here now we're going to a bit more stoichiometry, and this is what they love to test. Calculate the original concentration of the original vinegar solution in grams per litre. Okay. The number of moles in the original solution must be equal to the number of moles in a diluted solution. Okay, essentially what's happening here is we have a very high concentration solution and we're adding water in. The number of moles isn't changing, just the volume is. Therefore, the concentration is decreasing. Because mole equals CV, if we keep this one the same, number of moles isn't changing, and we increase volume, concentration has to go down. It's fairly simple. All right. So we use an equation because moles are the same. Concentration times volume at time 1 must equal concentration times volume at time 2, because moles to begin with equals moles to finish with. So C1V1 equals C2V2. We want to find C1. The volume of the original solution is 25 mils, and the volume of the dilute, as we mentioned at the start of the question, is 250 mils. And we just found C2. We just found the concentration of the dilute. So C1 times 0.025, which is 25 mils, equals, well, volume 2 is 250 mils, so 0.25 litres, times by 0.1016 molarity. That was our concentration. Therefore, we can do a bit of fancy work with a few calculators. 0.25 times 0.1 divided by 0.025 gives us 1.016 molarity. So just 10 times the amount that we found in the original spot. Okay, awesome. We've now found the concentration in moles per litre. The issue is we want to find the concentration in grams per litre. Okay, well, the molar mass of ethanoic acid is 60.1 grams. So what this is saying is for every mole of ethanoic acid we have, that's equivalent to 60.1 grams, all right? And if we look at this, if we do moles per litre times by grams per mole, we're actually going to get grams per litre because our mole, I messed up my animations here, but if we multiply this together, our mole cancels out with mole. So doing moles per litre, so concentration, times by molar mass, grams per mole, gives us grams per litre. So the concentration of the vinegar equals 1.016 moles per litre times 60.1 grams per mole, gives us 61.06 grams per litre. That is such a tough question. I apologise for how heavy that is, but this is the sort of level we want to be getting to when it comes to titration questions. Here, what I recommend doing is we've got a checklist. Okay, we want to highlight everything in the original thing. In the original question, it says dilute, so we're going to make sure we recognise that. But the biggest thing is it says in grams per litre. We can very easily find moles per litre, which is what we've done here. We found the moles per litre in the original vinegar solution. And then we just need to find a way to convert moles per litre into grams per litre. And that there is just through the molar mass. Awesome. So I'm just going to remove all of these annotations. Fantastic. Okay. So now I just want to explain why the vinegar was diluted. Okay. So this goes back to our titration principles. If the solution had not been diluted, the volume of vinegar needed to titrate the NaOH solution would be very small. This will result in greater error as one extra drop of titer would contain 10 times more molecules on average than the diluted solution. What this is saying is if you had a drop, so in a titration, we're essentially doing like a 1 drop at a time, right? And we're checking after each drop if the color of the solution, if the indicator has changed color to let us know that the solutions have reached their equivalence point. If we're using drops of a very high concentration, well, we're not gonna need many drops, but also that means 1 drop signifies a lot of molecules, and that can actually have a dramatic effect. And if we try and minimize the amount of molecules, the more we minimize the amount of molecules in a drop, the greater accuracy we're going to have. Ideally, in an ideal world, we could drop in 1 molecule at a time, and then we could work out exactly how many molecules we need. Obviously, dropping in 1 molecule at a time is going to take millennia, so we have to obviously balance. But ideally, the more diluted the solution, the more accurate our titration is. Final bit of question is, which of the following should the burette have been rinsed with? Okay, well, what do we know? We know, back from my explanation on errors, that the burette needs to be rinsed with the titer. It needs to be rinsed with whatever is being titrated. Therefore, the final rinse should be using the chemical the equipment is going to contain. The burette, in this example, houses the vinegar, the diluted vinegar solution. Therefore, we're going to use the diluted vinegar solution. So you're going to do the final rinse with whatever the solution whatever the equipment's used to contain. Awesome. Okay. Now on to spectroscopy. Now, guys, this is going to our last half an hour. I do apologize as this is tough work, but we're just going to run through it. Okay. IR spectroscopy is pretty cool. Essentially, what's happening is we are shining energy and shining light into a molecule, infrared light, and the bonds between the atoms of the molecule correspond, because they're like an OH bond is different from a CH bond. They're going to correspond to different energy, and they will absorb a different energy. So what this is, this spectra here, is essentially, at its very basic point, this is showing how much is absorbed. So up here, 0% absorbed, but like down here is almost 100%. And this is just saying that this energy level at around, I don't know, I think there's like maybe a 1900, 1700 per wave number per centimeter corresponds to the amount of energy required to make a C double bond O bond, so a double carbon oxygen bond, vibrate. So bonds will absorb different wavelengths of IR radiation, which excites the molecules. And spectroscopy, essentially, all it does is that it measures the amount of radiation absorbed and correlates that with the absorbers of known functional groups. So we've got a big database telling us that, okay, this functional group absorbs this much, this functional group absorbs this much, etc., etc. So then we run a separate molecule through IR, and it will produce a spectra like this. And therefore, we can compare it to what we know, and then work out what the atom actually is. Sorry, the molecule actually is. So we're looking at CO and OH. Now, OH is really cool. Now, when we're looking at this sort of data, we say from like here onwards, 1000 to the right, so all the way down to 100. This is the fingerprint region. This essentially just tells us like the bonds between hydrogen atoms and stuff. Like it's not that big a deal, and we don't really read this. We don't like it that much. Here, however, is where we get is the bread and butter of IR analysis. This jagged little thing here is the CH stretch. And this is just the bonds between carbons and hydrogens. This will should occur in all groups. This here, though, this like almost like parabolic looking arc is a bit different. This is the OH stretch. So this absorbance here represents the bond between an oxygen and a hydrogen. So if you see this parabola thing, it could what we're looking at would either be a alcohol, it could be a carboxylic acid, it could be those sort of things. So that's a strong peak at around 3,400. Okay. We also have at this peak here, this C, and that peak there represents CO. So if we have an OH group, we're also got to be bonded to a carbon. Therefore, we've got to have a CO group, and the CO group can belong to an alcohol, an ester, or an ether. So the big trough at OH. Sorry, at 3,400 represents an OH, which means this is either an acid or an alcohol. And because there's no other groups, like if it's an acid, we'd also expect a C double bond O. Well, there's no other groups, therefore this must be an alcohol. And as we can see down the bottom, this is in fact the IR spectrum of butan 1-ol. All right, okay. So that's like almost like a smile, I imagine, that OH. C double bond O is a bit different. And you can see at around 1,600 and 1,700, we have this bad boy here. It's almost like a sword pointing down. When we see this big point here that almost goes down to 100% absorbance, you know that it's a C double bond O. Now, what molecules have C double bond O? Well, we have aldehydes, ketones, and carboxylic acids. When we see this, okay, well, if it was a carboxylic acid, we'd have the OH thing we just discussed earlier. That would be in there. Therefore, it's not that one. Therefore, this is either a ketone or an aldehyde. Now, we don't really know. And in your data booklets, it will give you the bond. The section where it gives you the sort of bond that occurs alongside the wave number where it will occur, like that on the x-axis. But we can't really distinguish between ketones and aldehydes on this one. Therefore, we're going to use other spectra, which is what we'll come to in a bit. All right. The next one here is C double bond N. Like as you can see here, sorry, not C double bond N, C bonded with N. butylamine, or as we'd call it with IUPAC in Australia, we'd call it a butanamine. We have an NH2 that's connected to a carbon. Now, when you look at the data booklet, you see that this actually overlaps with OH, which is, a bit unfortunate. And people will be like, oh, how do I know which one's which? That's a bit different. Okay, so an OH group will almost always look like a parabola, like that, almost like very straight. But a NH, I don't know why, but N almost reminds me of like vampires. It's super strange, and the reason why I think that though is because this thing here, it's like a jagged little, like almost like vampire teeth, and that's how I remember it. OH looks like a smile, and then CN looks like vampire teeth. There, very diagnostic vampire fangs in 3,400. Even though it's at the same wave number as we'd expect a hydroxyl group to occur, we know for a fact, because of the vampire fangs, this is butanamine. Awesome. Okay, and we'll move on. Okay, so here is exactly what I was just talking about. At around 1,000, this is like the fingerprint region, we don't really care about it. At about like 1,700 or 1,600, we're going to have this C double bond O, this jagged bit like a sword right down. In VCE, we don't really care about C triple bonds. That doesn't really come up in spectra, but it could. So, but if anything they're going to give you will come up in the data booklet. So if it doesn't discuss the data booklet, you don't need to worry about it. Have that CH stretch we were talking about, and again, that OH stretch. The thing to note here is that in an alcohol, the OH stretch, that big parabola, is going to be much more left, and in a carboxylic acid, it's going to be further and further right, up until the point where it kind of might actually blend in with this CH stretch. Just to be warned. All right. Okay. Next up is NMR spectroscopy. So this here is a little more complicated. Nuclear magnetic resonance, NMR, is a technique that essentially analyzes the magnetic fields around the nuclei of atoms. So we send radio waves in, and the energy absorbed by the molecule, gives us an indication of the strength of like magnetic fields of individual atoms. It's a bit complicated, but essentially all you've got to know is that nucleons, so like protons and neutrons, have spin. This concept called spin, and spin generates a magnetic field, and we measure the difference in spin. Now there might not be a difference in spin if you've got like an equal number of protons and neutrons. Therefore, we use isomers, so isotypes with an odd number of nucleons. So we use carbon-13 and hydrogen-1, so carbon with one extra. So usually have carbon-12, which is 6 protons, 6 neutrons. We're using 6 protons, 7 neutrons, and hydrogen, which is usually 1 proton, 1 neutron. We're just using hydrogen as 1 proton. And so that's what C13 and H1 means. You don't really need to know more about it than that. But essentially, the NMR spectra, where the IR spectra produces a peak for every bond, the NMR spectra produces a peak for every environment. This is a bit crazy. Okay. Environments. So an environment is the surroundings of a particular atom in a molecule. What it's bonded to and what it's bonded to is bonded to. So different environments will produce different peaks. And for multiple carbons and hydrogen atoms in the same molecule, they're in the same environment if they have the same bonds and are bonded to carbon atoms with the same bonds. So if we have a look at it, this carbon here is bonded to 3 hydrogens and a carbon that's bonded to 2 hydrogens. That's our first carbon. That's our first environment. This carbon here is bonded to a carbon, bonded to 3 hydrogens, bonded to a carbon, bonded to double bonded to an oxygen, and also bonded to 2 hydrogens. That's our second environment. This carbon here, you can obviously tell it's unique. It's the only carbon that has a double bond to an oxygen. Now this carbon here is actually our 4th environment. People are like, but it's bonded to 3 hydrogens and bonded to another carbon. Why isn't it the same as our first one? Well, our first one is bonded to 3 hydrogens and then bonded to a carbon that's bonded to 2 hydrogens. This carbon here is bonded to 3 hydrogens and bonded to a carbon that's bonded to an oxygen. Therefore, we have 3 distinct carbon environments. A little tough, but they're to understand, but there's 4. There's There's 4 distinct carbon environments. All right. Next up are our hydrogen environments. Okay. Well, this hydrogen bonded to this carbon here is bonded to a carbon bonded to 2 hydrogens. That hydrogen's the same, that hydrogen's the same. So all of these are the same environment. Now, if we have a look for our next one, this hydrogen is bonded to a carbon that's in a different environment to this first one. Because it's in a different environment, this carbon here, sorry, this hydrogen here has to be a different environment to that one there, but all of these ones are the same. And finally, as I'm sure you'll be able to tell, this hydrogen down here is bonded to a carbon that's bonded to a CH3, a CO, CH3. So this here is also a unique environment. Therefore, we've got 4 carbon environments and 3 hydrogen environments. All right, so here's a bit of a question that I'm just going to run us through. Name and identify the number of carbon and hydrogen environments in each of the following molecules. Okay. This here is 1-chloropropane. It's propane, so CH3, C3H, usually it's C3H8, if I'm not mistaken. But instead of a hydrogen on the first carbon, we also have a chlorine. Okay. What do we have? We have 3 unique carbon environments. First off, we have a carbon bonded to 3 hydrogens and CH2, CH2Cl. A middle carbon, you can tell it's different. And this final carbon, if there was a hydrogen here instead of a chlorine, it would be identical to that one on the left. But the issue is it's the only carbon bonded to a chlorine, therefore it's in its unique environment. There's 3 carbon environments. Likewise, there are 3 unique hydrogen environments. This one bonded on the end, so these hydrogens are bonded to a carbon bonded to 2 other hydrogens. The ones in the middle is bonded to carbon bonded to 2 other carbons. And this one in the end is hydrogens, are the only hydrogens bonded to a carbon bonded to chlorine. A bit complicated. This here now is probably the hardest sort of molecule that ever ask you to name. But this here is 3-hydroxy 2,2-dimethylpropanoic acid. Okay, we're naming this. How do we name it? Okay, first off, we look for the longest chain. Now, the longest chain also always includes our functional groups. Here's an OH. Here's our longest chain. Here's our this is our carboxyls. This is propanoic acid. On our 3rd carbon, so this is 1, 2, 3, we have a hydroxyl group, and on our 2nd carbon, we have 2 methyl groups. So here we have on the 3rd carbon, 3-hydroxy. On the 2nd carbon, we've got 2 methyl groups, 2,2-dimethyl-propanoic acid. Now, the thing to note is that we've got to put this in alphabetical order. But we don't include any prefixes in alphabetical order. So H comes before M in the alphabet, therefore we're talking about the hydroxy first. If it was, for example, ethanol, like diethyl, well then the ethyl would go first. We'd have 2,2-ethyl, 3-hydroxy. Just something to make clear. All right. There's 4 unique carbon environments. You can see that this one here is unique, so only one bonded to 4 different carbons. This is the only one bonded to 2 oxygens, and this one here is bonded to 1 oxygen, so they're all entirely unique. Finally, if we look at these ones, these 2 are also the only carbons bonded to 3 hydrogen, so they're unique, but these 2 are also indistinguishable, they're identical. So here we have our 4 carbon environments. 4 carbon environments and 5 carbons. There was just a question about will we lose marks if it's not alphabetical order? Technically, yes, but I would definitely bet against you ever seeing a question as hard as this, getting you to name it. They may give it to you in like an example for you to do something with it, but I doubt they'd ever get you to name it. Okay, so now when we're looking at hydrogens, we do the same thing. Okay, so we can see that these hydrogens here are all identical because they're all bonded to that carbon, and these hydrogens here are all bonded to that carbon. And because these 2 carbons are identical, these 6 hydrogens are all identical as well. The classic stitch up here is forgetting about this hydrogen here and this hydrogen here. Now these are both separate. This hydrogen is bonded to an oxygen bonded to CO. This is just bonded to an oxygen bonded to CH2, but also these 2 hydrogens are in its own environment. Therefore, there are 4 separate hydrogen environments to that one as well. Super tough. That's the hardest question I possibly could have think of to ask about that. essentially, this is NMR. So we have carbon-13 NMR, where we look at the number of carbon environments, and proton NMR, sorry, hydrogen NMR, where we look at the number of hydrogen environments. Simple enough. Okay. Here is our data that they give us. So RCH3 just means carbon bonded to 3 hydrogens bonded to more carbons, occurs at 8 to 25, etc., etc. So here, both of these things occur beneath 20. And I think it's fairly safe to say that C1 and C4, these 2 peaks, are both representative of RCH3. Only issue here is, although they're both in the same area, they're not obviously not the same environment. Otherwise, there'd only be 1 peak. Here at 60, we could be this here, which is a halo alkane. Unlikely. We're more likely to be RCH. Find this one down here at 170. We're likely looking at something like a carboxylic acid, or the same sort of thing there, or an ester. So if we have a look, this here is actually an ester. So here's C1, which is CH3. C4 is CH3 as well. So you can see C1 and C4 both fit into here, but C1 is bonded to a carbon that's bonded to an oxygen, whereas C4 is bonded to carbon bonded to hydrogens. C3 is bonded to an oxygen and bonded to another carbon, which means it puts us at 60, which puts us actually at this one here, even though it's not OH. And finally, C2 is bonded to an oxygen, 2 oxygens, which is in fact this one down here. So that's how you do it, which is why often you need multiple spectra to actually be able to work out a question. Okay, NMR, we use this thing called tetramethylsilane. This, whenever you see that, it just means that's 0 parts per million. It's just used as a reference point. Hydrogen NMR will have splitting, essentially, so the peaks of the hydrogen NMR will split n+1 times the n amount of hydrogens in a different environment bonded to adjacent carbon atoms. So all that's saying is if you have 7 splits in the peak, therefore there are 6 hydrogens that are different, that are not the same as the one that we're looking at, connected to carbon atoms bonded to the carbon atom that hydrogen we're looking at is bonded to. Bit complex, again, something to go over. Here's exactly what I'm talking about. Okay, so these are both identical in chemical formula, so C2H4Cl, but we've got the Cl's at different points. For here, on the one left, 1,2-dichloroethane, these hydrogens are all identical, therefore we're going to have 1 peak at 3.73. Here, it's a bit different. Our 2 chlorines are both on the same atom, so it's 1,1-dichloroethane. Well, here is, there's 2 environments. There's a hydrogen bonded to a carbon, bonded to 2 other hydrogens, and a hydrogen bonded to a carbon, bonded to 2 chlorines. If we're looking at, first off, these hydrogens here, well, they're going to be fairly lower if we look at the data booklet, and it splits twice. Why? Because n+1 rule is going to split n+1 times, where n is the number of hydrogens of a different environment bonded to adjacent atoms. There's only 1 other hydrogen bonded to an adjacent carbon. Therefore, it splits twice, 1 + 1. Here, if we have a look at this hydrogen, well, there's 3 hydrogens that are adjacent. Therefore, it splits 3 + 1 times, splits 4 times. There's 4 little peaks there. That's essentially the basis of the rules. Okay. Here's a question that also I'm going to rush through because I want to get onto food chem. Essentially, we have 3 structural isomers. They're all C3H6O. This is propanol, propanone, and prop-2N1-ol. The skeletal structure for the aldehyde propanol is above, top right. So write the semi-structural formula for the ketone, draw the structural formula for propan-2-ol, and consider the NMR spectra. Okay. So write the semi-structural formula for the ketone isomer propane. Simple enough. Propanone is this, and it's a ketone, so the double bond O is in the middle. So CH3, CO, CH3. Easy enough. 1 mark there, quite simply. Draw the structural formula for prop-2N1-ol. So prop-2N1-ol. So on the first carbon, we have our OH on both of these 2 examples. And then on our second carbon, we have that double carbon-carbon double bond. Easy enough. Nice 2 marks there. All right. As you can see, the average mark is given to you. Or if you go to the VC exam reports, I really recommend going. Average mark is given to you. So the average mark here in total was 1.3 out of those 2. So this is really where you can get your easy marks. Okay. Now, for the following NMR spectra, identify which of the 3 named isomers of C3H6O produces spectra and justify your answer by referencing the carbon and the hydrogen spectra. Okay. Well, if there's 2 environments, there's 2 carbon environments, right? So one is at 205 parts per million, so all the way down here. And if you look at your data booklet, you'll see that actually represents a ketone. And there's also 1 proton environment, which means all of these 6 hydrogens have to be identical. Therefore, it's symmetrical. Therefore, the answer is propanone. If we have a look at it, if I draw it out, you can see we have 2 different carbon environments. So here's 1, here's 2. This carbon there is identical to that first one, and the hydrogens are all going to be exactly the same. Okay, the other way we can answer this question is we could say, well, I don't know if it's a ketone, the aldehyde, or the alcohol, so let's do process of elimination. Okay, so propanol, so an alcohol would have at least 2 hydrogen peaks. So it would have it would have at least 2, rather, hydrogen peaks, because there'll be a peaks for the C between the C and the H, and for the H connected to the O. Propanol would have at least 2 hydrogen peaks as well, because you'd have the CH3 and CH2, but you'd also have extra ones as well, because you'd have the hydrogen connected to the carbon connected to the double bond O. Therefore, it can't be propanol, it can't be propanol, therefore it's got to be propanone. That's how we go about it. That's a pretty hard question, so really well done if you followed me through this part. Okay. A final bit, we've got 15 minutes left, so I'm just going to keep smashing through, is fuels. Okay. We have fossil fuels and biofuels. Fossil fuels undergo combustion to produce CO2 and H2O, and these contribute to our environmental effects: greenhouse effect, desulfurization, increased ozone levels, and acid rain. Biofuels are same sort of thing. We combust them to produce energy, to like spin a turbine or whatever, but these are considered carbon neutral because they come from the environment. They're renewable in the sense that the carbon neutral in the sense that the carbon it takes to grow them, the carbon dioxide released, burning them, is counteracted or bounced by the carbon required to produce them. And they're actually very cheap. We have biomass / biogas where we combust like wood and crops and that sort of stuff. And biomass, you don't necessarily have to combust it, but we can actually use bacteria to make biomass, like your waste, like even like animal feces or animal oils or whatever. You can actually make it with bacteria to become gases like methane and ethanol. And ethanol we can use to power cars. Bioethanol, or sugar from some crops, is converted to ethanol and it burns very clearly, is more biodegradable. But it really attracts water. It's hygroscopic. That means it attracts water, which means normal fuels are like hydrocarbons, which means they're very they don't like water that much, which means it's super, like water will stay away, so our fuel lines will remain very, very clear of water. But with ethanol, our fuel lines may get impacted with water. Biodiesel is pretty cool. So we have triglycerides, which we're going to talk about in a sec, and they're reacted with an alcohol, usually methanol, to produce biodiesel. So essentially it's an ester. So we have our alcohol part is really short, so it's methyl, and then our carbon tail can be like 20 carbons long. So these are very similar to petrofuels, like petrodiesel. But the issue is the ester link there means different bonds can be formed than if it's just a hydrocarbon. More energy is required, which is fantastic. It means it's got a much higher boiling point. But at cold temperatures, that means it's going to flow very slowly. And in the Arctic and stuff, it can actually like completely freeze. Okay, final part, food chemistry. Pretty basic stuff. You guys should know this. Should have just covered this, but there's a few basic ideas. We have proteins. Proteins contain an amine and a carboxyl function group. So on one side there's an amine, one side there's a protein. Sorry, one side there's an amine, one side there's a carboxyl. To add proteins together, so dipeptide, we react in a hydrolysis reaction, a condensation reaction, the OH group and the H of the NH2 group, which joins the carbon that bonded to the double bonded to the oxygen, joins that to the nitrogen. That's called a peptide link. And there's a list of all of them in your data booklet, and they all have this R group that are there. They're all different. And that R group, for example, in alanine is just CH3. In arginine is this really long chain. In asparagine, it's this chain here, which is a bit more complicated. So all of these amino acids are different, and they contribute to proteins. All right, so the bonding of proteins are pretty cool, and we have 4 levels of bonding. Primary structure is just which amino acids are being used. So, like, are we using like glycine, then asparagine, and then et cetera, et cetera, et cetera. And that's just the order of the amino acids in a protein, because the order of the amino acids will change in every protein. A secondary structure is how the chain spirals. So the chain will start to bend, and it will either pleat, which is called beta pleating, or it will spiral into an alpha helice. And that's just caused by hydrogen bonds within like adjacent amino acids. Our tertiary structure is a bit cooler, and this is what happens is interactions between those R groups I was talking about. So the R groups that have oxygens can actually form like hydrogen bonds between each other, which will cause the entire chain. So it could be on amino acid like 12 and amino acid 30, and it'll cause the chain to bend in. Sulfur, this is a weird one. Sulfur will bond with other sulfur molecules, sulfur atoms, to create a disulfide bridge. Hydrophobic groups, so lots of CHs with no sort of any other atoms, will try bend inwards to try like save themselves from water, and ionic bonds can also occur, and hydrophilic reactions can also occur. Okay, ternary structures, so the 4th level, is just there's different proteins that will interact with other peptide chains. So the bonding there is just the bonding between those different chains. Okay, polysaccharides are just sugar molecules, and polysaccharides, a monosaccharide is just your ordinary sugar, your ordinary glucose, and polysaccharides are just multiple glucose joined together by what's called a glycosidic link, which is actually an ether link. It's the same thing. We call it in food a glycosidic link. So each of these little dots, like little shapes there are glucose molecules. So the difference between all of these, this is starch. Starch is can be made of amylose, which is just one straight chain, and amylopectin. Now we require enzymes to break this stuff down. So with amylose, it can break off one at a time. So break off that one, then break off that one, break off that one. With amylopectin, at the same time, you can break off all of these end molecules, monosaccharides. So this is broken down much quicker. Glycogen is essentially how we store sugar in our liver, and this is much more branched, as you can see. And cellulose is just glucose as well, but this is fiber. This is what we have like on our veggies, and because it's so compact like this, we don't actually have the right enzymes to break it down, which I'm going to talk about in just a second. Okay, the next thing to talk about is fats and oils. So fats and oils are very similar structures, except fats are solid, and then oils are liquid at the same temperature. Okay, so a triglyceride is a molecule that has 3 fatty acids. This here is a fatty acid. These are fatty acids, and this is glycerol, where we've got 3 hydroxyl groups. And what happens is we produce 3 waters out of each of these spots, and this is a triglyceride. Awesome. And that's triglyceride. So the thing to note is that as the number of carbons increases, the melting point increases. But when in our fatty acids, when we have double bonds, the presence of double bonds decreases the number of hydrogens, which decreases the number of dispersion forces that confirm. But the presence of double bonds in a long chain actually causes the chain to like kink a bit, like bend around. And because double bonds in fatty acids will produce more and more like kinks in the chain, actually it really means that these unsaturated, so polyunsaturated and monounsaturated, means they're having double bonds. These fatty acids are going to be oils, whereas fats are typically, which are solids, are going to be saturated. Awesome. Okay. So the final few bits here, we've got the last 5 minutes, and we're going to just, be happy to stay behind us, answer a few questions. But metabolism is a breakdown of food. And essentially it's brought about by enzyme catalyzed hydrolysis. So carbohydrates polysaccharides will break down to monosaccharides. and then gets stored again as polysaccharides. Triglycerides gets broken down by hydrolysis into glycerol and fatty acids. It undergoes condensation to become triglycerides again when we, like in our bodies. Proteins will be broken down into amino acids by hydrolysis. Okay. Enzymes are pretty cool. So enzymes, we have a molecule that binds very specifically for a substrate. It binds into this site called the active site, this substrate. This is a molecule. We use this thing called the lock and key molecule, where the substrate fits like a key into the active site. An enzyme is a catalyst essentially, and it's also a protein. So an enzyme doesn't affect equilibrium and they're not used up, but due to the 3D nature of the protein, enzymes are only able to catalyze reactions in specific environments. This is because when we increase temperature, for example, the temperature of the human body is like 37 degrees Celsius. When we increase temperature, well, that causes even though we'd expect rate of reaction to increase the more we increase temperature causes the bonds between proteins, so between amino acids and the proteins, to become more and more unstable up until they break. Which is why when you have an egg, like you crack an egg into a pan, it's clear, but as you heat it up, it becomes white, which is why that's essentially the proteins breaking down, which is called denaturation. So after 37 degrees Celsius, our rate of reaction decreases with enzymes because our enzymes no longer work. They've lost their 3D shape. This is the same thing with pH. So we have this thing called fluid ions, where it's a perfect pH. An amino acid is a base and an acid at the same time. So it accepts the extra hydrogen from the environment and also donates a hydrogen. And changing your pH will change essentially the R chains. Will change their if they're an acid acting as an acid or a base, which will essentially change the molecule, will change the tertiary structure of the molecule, which means if you change the pH, different things will happen. So for example, enzymes that work in your stomach that are very acidic won't work anywhere else in your body because the rest of your body is very basic. Awesome. Okay, final stretch, guys. I do apologize. This is just a question here that I'm just going to brush over just so we can move on to calorimetry, but in the recording, feel free to pause this, and it's just about different enzymes. So I'm just going to, there's just time to pause it if you are doing that question. Okay. Energy content is the next big thing. So different foods will have different energy content, and energy value. Energy content is the amount of energy a particular form of food will release when combusted, but the energy value is how much we get, because we don't actually absorb all of the energy of our food. All right, calorimetry is essentially the method of measuring the heat energy released and absorbed by a chemical reaction. And there's two types: there's bomb and solution. Solution is what we do in a classroom. Bomb is what they do on an industrial level. So whenever we burn some food in a machine, right, some of the energy is going to be lost to thermal energy or whatever. So each apparatus has a unique calibration factor. So what we do is usually we burn a chemical, we put in electricity of a known energy amount, and we calculate the temperature increase of water. And then we can work out the theoretical and the actual, and we use the difference to calculate a calibration factor. And the calibration factor, we can then use that calibration factor because it tells us how much energy is lost every time we use it. And then we burn food in this thing, we apply the calibration factor, then it tells us how much energy a piece of food actually has. So here is a perfect question. Benzoic acid may be used in a bomb calorimeter. Here's the solution. 1.845 grams of benzoic acid was burnt and the temp was increased by 33.53. Okay, so 2 moles of benzoic acid produces 6,454 kilojoules. The mass of benzoic acid is mole times by molar mass. Therefore, the mass of benzoic acid we have is 244. Of 2 moles is 244 grams. Therefore, 244 grams correlates to 6,454 kilojoules released. 1 gram, we're going to divide both sides by 244. 1 gram corresponds to 26.54, and we have 1.845 grams to burn. Therefore, times both sides by 1.845. That's 49 kilojoules. Okay. Therefore, releasing 49 kilojoules. Determine the calibration factor. This is just a simple formula. Calibration factor equals energy divided by change in temperature. Well, we release 49.04 kilojoules, and the change in temperature was 33.53. That gives us that value there, 1.463 joules per kilojoules per degree Celsius. To put that into joules, we just times it by 1,000. Okay, so we found the calibration factor. We then have almost 6 grams of dried biscuit burnt, and we've got temperature increase. Calculate the energy content. Okay, energy content, we're going to use the same formula, but just reversed. Energy content equals calibration factor multiplied by change in temperature. 1,463 multiplied by change in temperature, which is just those numbers there, gives us 5,779 joules for the 5.59 grams of biscuit. Therefore, 5.59 corresponds to 5,779. 1 gram, divide both sides by 5.59, gives us 1,034 joules. Therefore, the energy content is divided by 1,000, 1.03 kilojoules per gram. Okay, awesome. Okay, essentially, we've gone through a few study tips, and I can summarize briefly, but what I'd love for everybody to do is there is a quick survey. I apologize that we're now out of time, but I think it's really important for everyone to just do this survey very quickly. I'm just popping into chat now. This just tells us, how today went. I do apologize, I've been a bit over time. I'm so sorry, there's just so much content to cover. But feel free, please do this survey for us. You get access to the recording if you need. Thank you very much for all your attention today. And if anyone has any more questions, feel free to pop them in chat. Awesome, thank you. You can hear by the end my voice is getting very hoarse. So I do apologize for rushing through that last bit, but you guys have just covered that, so I think that's okay.
Thanks, Josh. That was great.
No stress, thank you.
Yeah, thank you.
So if you guys do the form, so please make sure you do it because it's very important for Skyline. You get access to the recording, so you can go through and pause that to go through those questions that I missed and everything. So don't stress about that. Please make sure you do that form. Thank you for your kind words, everyone. I really appreciate it, and thank you for sticking by this entire time. I realize it's been very long, but I hope you guys got something out of that. Right. Again, make sure you do that form, and if you finish that form, feel free to head off. Thank you for all your time, everybody. And any questions, just feel free to stay behind a bit, and we can have a discussion. Oh, Leah, fantastic question. Related to the UCAT process, yeah. Okay, so guys, I just copy and paste the form again into the chat. You will receive a recording of the session. I think you just have to do the form. I've just posted the form into the chat again. Related to the UCAT process, yeah, mine was okay. I was very fortunate that I'd done a lot of stuff, UCAT sort of style questions unrelated to the UCAT, so that was okay. But it's pretty cool when it comes to interviews and stuff. Essentially, you will get offered an interview. I think this year will be different. I don't think you get offered an interview based on your ATAR, but for my year it was ATAR and UCAT, and then you sit and answer questions about like your experiences and what you do in certain situations. That's essentially how the UCAT works, the interviews work. based off your UCAT and your ATAR, which is what gets you into medicine. Yeah. No stress. Thank you very much for your time, everybody. Feel free to head off unless you've got any questions, and make sure you've just finished that form out. You'll get access to the recording through that. No stress. Thank you very much for your time. I'm not in control of if you get the PowerPoint or not. I can ask about it, but you know, if you get the PowerPoint, you can just scroll back through. Awesome. Thanks very much for your time, everybody. And I'll see you all later unless you've got any more questions. Awesome. Make sure you fill out the form, and otherwise, thank you very much for your attendance.